There's a mysterious radio signal stretching across the universe, whispering secrets from a time we've never seen. It's not a message from aliens or some artificial transmission, it's something far more intriguing. A signal from the most abundant element in the cosmos, hydrogen. More specifically, it's a faint, stretched-out version of a radio wave called the 21 centimeters hydrogen line. But here's where it gets weird. Something is distorting this signal in ways we don't fully understand. Scientists expected one thing, but when they finally detected this ancient whisper from the universe's past, it was different, far too different. It was redshifted beyond what models predicted, hinting at something massive we might have completely overlooked. What could have changed the very fabric of the cosmos so early on? And what does this tell us about the universe's first moments? To understand why this is such a big deal, we need to talk about what the 21 centimeters hydrogen line actually is. See, hydrogen is everywhere. It makes up about 75% of the normal matter in the universe, and in the early days, before stars and galaxies, the cosmos was basically a vast ocean of neutral hydrogen atoms. These atoms have a unique property. Their single proton and electron can flip between two energy states. When an atom's electron switches from a higher energy state to a lower energy one, it emits a tiny pulse of radio light, specifically at a wavelength of 21 centimeters. It's like hydrogen's natural fingerprint, a way for scientists to track where it exists in space and time. Normally, if you were in space with a perfect radio antenna, you'd pick up these signals exactly at 21 centimeters. But because the universe is expanding, light from distant objects gets stretched. This is what we call redshift. The farther back in time we look, the more stretched out the 21 centimeters signals should be. Scientists predicted they'd see a smooth, predictable curve in this signal, reflecting the transition from a dark, hydrogen-filled cosmos to one lit up by the first stars and galaxies. But when astronomers actually measured it, something was off. Instead of the expected signal, they found a much deeper dip, like a fingerprint in the cosmic background that shouldn't have been there. This was first detected by an experiment called EDGES, experiment to detect the global EOR signature, a small but incredibly precise radio telescope in the Australian outback. In 2018, EDGES picked up a strange anomaly in the 21 centimeter signal. It was not only redshifted, but it was also significantly stronger than expected. The dip was too deep, meaning that something had cooled the hydrogen more than our current models predict. This was a massive problem for cosmologists. The universe should have been at a certain temperature at that time, warmed slightly by the cosmic microwave background (CMB), the afterglow of the Big Bang. But this deep 21 centimeters absorption suggested that the hydrogen gas was colder than it should have been. Why? There are a few possibilities, but none of them are simple. One idea is that dark matter could be responsible. Dark matter doesn't interact with light, which makes it invisible, but if it interacts with normal matter in a way we haven't yet discovered, it might have been sapping energy from the hydrogen, cooling it down more than expected. If true, this would be groundbreaking. It would mean we've finally detected evidence of dark matter's interaction with normal atoms, something physicists have been searching for decades. Another theory is that the first stars, when they formed, might have behaved differently than we thought. Normally, as the first stars ignited, they emitted high-energy ultraviolet light, which would have interacted with the hydrogen and changed its signal. But for the EDGES detection to make sense, these first stars would have had to form much earlier or have been much more energetic than our models suggest. And then there's the even wilder possibility. Maybe something completely unknown was happening in the early universe. Maybe new physics, something beyond our current understanding, was shaping how hydrogen behaved. What makes this even more frustrating is that the EDGES experiment is just one detection. Other telescopes haven't yet confirmed it, though researchers are building more sensitive experiments to check. If this strange 21 centimeters dip is real, it could be one of the biggest discoveries in cosmology, forcing us to rethink the fundamental physics of the early universe. If it turns out to be an error, then it's back to the drawing board. But let's assume for a moment that it's real. What does that mean? Well, it could be a direct glimpse into an era we've never been able to study before, the cosmic dawn, when the very first structures in the universe were taking shape. Before stars and galaxies, there was only hydrogen and dark matter, locked in a delicate cosmic dance shaped by gravity. If something unexpected happened during this time, it could change everything we think we know about how the universe evolved. Think about that for a second. We've mapped out so much of the universe. We've seen the cosmic microwave background, the faint glow of the Big Bang. We've observed galaxies forming, stars dying, black holes merging. But this is different. This is a window into a time before any of that. A time when the universe was dark, cold, and waiting for the first sparks of light. And the mystery isn't just about what happened, it's about what's still out there. If dark matter really did play a role in cooling the hydrogen, then that means dark matter is more than just a silent observer. It's an active participant in shaping the universe. If the first stars were more powerful than we thought, then our models of how elements formed might need an update. And if something completely unknown was responsible, then we might be on the edge of discovering brand new physics. The search for answers is just beginning. New experiments are being planned, bigger telescopes are coming online, and astronomers are digging deeper into the data. The 21 cm hydrogen line is one of the most promising tools we have to study the hidden history of the universe. And if this redshifted anomaly holds up, it could lead to discoveries we can't even imagine yet. So what's next? Scientists need to confirm EDGE's findings with independent experiments. If they do, then we'll have a genuine mystery on our hands, one that could rewrite our understanding of the early universe. If they don't, then we'll still have learned something valuable about how difficult it is to measure such faint signals. Either way, the quest to understand the cosmic dawn is far from over. And that's the real beauty of space mysteries. Every time we think we have the answers, the universe throws something unexpected at us. The redshifted 21 cm hydrogen line is just one piece of the puzzle, but it might be one of the most important. Because if we can figure out what's hiding in this signal, we might finally unlock the secrets of how the universe became what it is today. The search for answers doesn't stop with just one strange signal. If the EDGE's detection is correct, it raises a flood of new questions about the early universe. How did this unexpected cooling happen? What forces could have influenced the hydrogen at this time? And most importantly, what else are we missing? To truly grasp the implications of this redshifted 21 cm signal, we need to go deeper into the physics of the early cosmos. Right after the Big Bang, the universe was a chaotic, high-energy soup of particles. Over time, as it expanded and cooled, protons and electrons combined to form neutral hydrogen. This was the beginning of what we call the Dark Ages, a period when the universe had no stars, no galaxies, just a vast, featureless sea of hydrogen and dark matter. During this era, the universe was governed by gravity, with dark matter forming invisible scaffolding that would eventually guide the formation of galaxies. But at this point, there was no light. Nothing was hot enough to shine. The only radiation filling space was the faint afterglow of the Big Bang, the cosmic microwave background, CMB. And this is where things get interesting. The 21 cm hydrogen line is affected by its interaction with this background radiation. If hydrogen is at a higher temperature than the surrounding environment, it will emit the 21 cm signal. If it's at a lower temperature, it will absorb some of the CMB radiation, creating a dip in the radio spectrum. What EDGE's found was an unexpectedly deep absorption, which means the hydrogen was colder than expected. One possibility for this unexpected cooling is that dark matter was interacting with regular matter in an unknown way. Normally, dark matter is thought to be nearly invisible, affecting the universe only through gravity. But what if it could actually transfer energy? If dark matter particles had even a tiny ability to interact with hydrogen, they could have pulled energy away, making the gas cooler than it should have been. This would be one of the first direct signs that dark matter isn't just a passive force but an active player in shaping the cosmos. This theory was proposed shortly after the EDGE's results were announced, and it's incredibly exciting because it provides a testable prediction. If dark matter was cooling hydrogen, the effect should be stronger for lighter dark matter particles. That means future experiments could measure this cooling effect in more detail, helping us pin down the nature of dark matter itself. But dark matter isn't the only explanation. Another theory suggests that the first stars might have formed much earlier than we thought. The moment these stars began shining, they released ultraviolet radiation, which could have affected hydrogen in unpredictable ways. Normally, this process, called Lyman-alpha coupling, should have left a different signature in the 21 cm signal, but if these stars were forming in strange, extreme conditions, it might have changed the expected pattern. This idea leads to even bigger questions. Were the first stars fundamentally different from the ones we see today? Were they more massive, burning hotter and dying faster? Could they have influenced the birth of galaxies in ways we haven't accounted for? If the edge's signal is real, it means our models of the first stars might be missing something crucial. And then there's the most unsettling possibility. Maybe this anomaly is pointing to entirely new physics. Some researchers have proposed that the edge's signal could be evidence of exotic particles we haven't discovered yet, like axions or other theoretical particles that could have influenced hydrogen's behavior in unexpected ways. If true, this would mean rewriting fundamental physics and possibly opening the door to a new understanding of the forces that shape the universe. But before we jump to conclusions, there's still one major issue. The edge's result hasn't been independently confirmed. Science doesn't work on single detections, it requires repeated, independent verification. Other telescopes, like the Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SK, are being developed to scan the sky for similar signals. If they detect the same strange redshifted 21 cm dip, then we'll know we're dealing with something real. If they don't, then it might have been an experimental error. This uncertainty is what makes space mysteries so thrilling. Every discovery has the potential to either change everything we know or reveal the limits of our current understanding. And no matter which way it goes, we learn something new. If the 21 cm anomaly is confirmed, it could be one of the biggest breakthroughs in cosmology. If it isn't, then it means our instruments need refining. But even that teaches us more about the challenges of studying the early universe. Regardless of the outcome, the study of the 21 cm hydrogen line is just beginning. Even if Edge's anomaly turns out to be a false alarm, future experiments will still use this signal to map the first structures in the universe. The cosmic dark ages are one of the last unexplored frontiers in astronomy, and the redshifted 21 cm line is our best tool for unlocking its secrets. Think about what this means. For the first time, we might be able to observe not just distant galaxies, but the very conditions that led to their formation. We might finally understand how the first cosmic structures emerged, how dark matter shaped the universe, and whether unknown physics played a role in the earliest moments of time. And this is just one mystery among many. The deeper we look, the more questions arise. The early universe is full of unknowns, from the nature of inflation to the first black holes, the role of dark energy, and the origins of cosmic magnetism. The redshifted 21 cm hydrogen line is just one clue in a much larger puzzle, but it's one of the most important. Because if we can unlock its secrets, we'll be looking directly into the universe's deepest past, back to a time before stars, before galaxies, before everything we see today. And that's why this mystery is so important. It's not just about one strange signal, it's about understanding the forces that made the universe what it is. If this signal is real, it could rewrite our understanding of cosmology, physics, and even the nature of reality itself. If it's not, then the search continues, pushing us toward even bigger discoveries. Either way, we're only at the beginning of the journey. The search for answers doesn't stop with just this one anomaly. If the redshifted 21 cm hydrogen line is revealing something unexpected, it could be pointing to an even bigger mystery, one that reaches beyond our current understanding of cosmology. Because when you step back and think about it, this signal is unlike anything else we've used to study the universe. It's not like looking at galaxies, which shine brightly with the light of billions of stars. It's not like the cosmic microwave background, which is the remnant glow of the Big Bang itself. Instead, this signal is coming from a time before any of that, before light even existed in the universe. It's a whisper from the dark ages, and the fact that it doesn't match our expectations means there's something we're missing. One of the most fascinating possibilities is that this anomaly is tied to the nature of dark matter itself. For decades, we've known that dark matter must exist because of the way galaxies move. Without it, the stars and galaxies would be flying apart, unable to hold together under normal gravity. But despite all the evidence for dark matter's existence, we still have no direct proof of what it actually is. It doesn't emit light, it doesn't interact with regular matter in any obvious way, at least, not in a way we've been able to detect. But what if this redshifted 21 cm signal is the first sign that dark matter isn't just a passive force? If dark matter was interacting with hydrogen in the early universe, cooling it down more than expected, it could mean dark matter has properties we never imagined. This could be the first real clue that dark matter is doing something beyond just shaping galaxies. It could be influencing ordinary matter in ways we never realized. The implications of this are staggering. If dark matter is interacting with regular matter, even slightly, it could completely change our understanding of how the universe evolved. It could mean that dark matter played a role in forming the first stars and galaxies, guiding the evolution of everything we see today. And if we can prove that dark matter is cooling hydrogen, it could open the door to a whole new branch of physics, one that connects the unseen world of dark matter with the normal matter we experience every day. But there's another possibility, one that's just as exciting but even more mysterious. What if this anomaly isn't about dark matter at all? What if it's revealing something about the nature of the universe itself? Some researchers have speculated that the edge's signal could be pointing to a fundamental flaw in our understanding of physics. The early universe was supposed to be relatively simple, just a vast expanse of hydrogen, cooling slowly over millions of years until the first stars ignited. But if the hydrogen was colder than expected, it could mean that something was removing energy from it, something we don't yet understand. One radical idea is that the laws of physics themselves might have been slightly different in the early universe. This could mean that fundamental constants, like the strength of electromagnetism or the properties of gravity, weren't quite the same back then as they are today. If true, this would mean that the universe has evolved in ways we never anticipated, and that the basic rules governing reality might not be as fixed as we thought. Another possibility is that exotic particles, beyond the ones we know about, were influencing the hydrogen in some unknown way. Some scientists have proposed that axions, a hypothetical type of particle that might solve the mystery of dark matter, could have played a role in the early universe. If axions interacted with hydrogen, they could have changed its temperature, creating the anomaly we see in the 21 cm signal. But here's the problem: all of these theories are just that, theories. Until we have more data, we can't say for sure what's causing this strange signal. And that's why astronomers around the world are racing to confirm the edge's result. New telescopes are being built to scan the sky with even greater precision. The Hydrogen Epoch of Reionization Array, HERA, for example, is designed to measure the 21 cm signal across vast stretches of cosmic time. If it detects the same anomaly as edges, then we'll know we're dealing with something real. But if it doesn't, then the mystery deepens. The Square Kilometer Array, SKA, one of the most ambitious radio telescopes ever planned, will eventually give us an even more detailed map of the early universe. With thousands of antennas spread across multiple continents, it will be able to detect the faintest whispers of hydrogen from billions of years ago. If the SKA confirms this strange 21 cm absorption dip, then we'll have undeniable proof that something unusual happened in the early universe. And even if these telescopes don't confirm the edge's result, that doesn't mean the mystery is over. It could simply mean that we need better instruments, more precise measurements, and new ways of looking at the data. Because one thing is certain: if the early universe really was colder than expected, it changes everything. Think about what this means. This isn't just about one strange signal. It's about the fundamental nature of the cosmos. It's about the forces that shape the first galaxies, the hidden properties of dark matter, and the possibility that our entire understanding of physics might need to be rewritten. And that's the beauty of space mysteries. Every answer leads to more questions. Every discovery opens new doors. The redshifted 21 centimeters hydrogen line is just one piece of a much larger puzzle, but it's a piece that could change our entire perspective on the universe. So what happens next? The search continues. Scientists are building better telescopes, analyzing more data, and testing new theories. And with every new piece of evidence, we get closer to the truth. Whether this signal turns out to be the first sign of new physics or just an unexplained anomaly, one thing is certain: the universe still has secrets left to reveal. And that's why we keep looking. Because somewhere out there, beyond the reach of our telescopes, beyond the limits of our understanding, the answers are waiting. And when we finally find them, they might change everything we thought we knew about the cosmos. But let's take a step back for a moment and really appreciate just how profound this discovery could be. The redshifted 21 centimeters hydrogen line isn't just another signal in the vast sea of cosmic radiation. It's a direct imprint of the early universe, a fossilized record of the time before the first stars were even born. If this anomaly is real, it means that something fundamental, something that shaped the very structure of the cosmos, was at play. And yet, despite all our theories, we still don't know exactly what that something is. To truly grasp the significance of this mystery, we have to go back to the very beginning, the moments after the Big Bang. The universe was a hot, dense plasma, a chaotic soup of particles. It wasn't until around 380,000 years later that things settled enough for neutral hydrogen to form, leading to what we call the cosmic dark ages. This was a time before stars, before galaxies, before the brilliant light of the cosmos as we know it. The only thing filling space was a vast, nearly uniform ocean of hydrogen gas, quietly waiting for the forces of gravity to sculpt it into the first structures of the universe. During this era, the hydrogen atoms absorbed and emitted light at a very specific wavelength, 21 centimeters. This signal was a fingerprint of the universe at that time, a silent radio whisper from the dawn of everything. Over billions of years, as the universe expanded, this signal was stretched, redshifted, and became incredibly faint. And now, with advanced radio telescopes, we can finally tune in and listen to that whisper. But what we hear doesn't match what we expected. The anomaly detected by the EDGES experiment suggests that the early hydrogen gas was colder than our models predicted. And that's where the mystery deepens. Something must have been cooling the hydrogen, but we don't know what. Could it be interactions with dark matter? Could it be an undiscovered force at play in the early universe? Or could it be something even stranger, something that defies all our current understanding of physics? One of the most intriguing possibilities is that dark matter played a direct role in cooling the hydrogen gas. This would be groundbreaking because, until now, dark matter has been thought to be invisible. In every sense, it doesn't emit, absorb, or interact with electromagnetic radiation. But if dark matter had even the slightest ability to transfer energy to hydrogen, it could explain why the 21 centimeters signal appears the way it does. Some scientists suggest that dark matter particles might have had a tiny charge or some kind of interaction with normal matter that we haven't detected yet. If true, this could revolutionize our entire concept of dark matter, turning it from a silent spectator of the universe into an active participant in cosmic evolution. Another idea is that the cooling effect could be caused by an unknown form of exotic physics. Perhaps a new particle, one that we haven't discovered yet, was present in the early universe, stealing energy from the hydrogen gas in ways we don't yet understand. If such a particle exists, it would be one of the biggest discoveries in modern physics, potentially solving multiple cosmic mysteries at once. But there's another possibility, one that challenges the very fabric of our understanding of the cosmos. What if the anomaly in the 21 centimeters signal isn't caused by something new, but rather, by something wrong in our current models? What if the fundamental constants of physics were different in the past? This idea is radical, but it's not entirely out of the question. The laws of physics are based on certain fundamental constants, things like the speed of light, the strength of gravity, and the fine structure constant, which governs the strength of electromagnetic interactions. These constants are assumed to be unchanging throughout time, but what if they weren't? What if, in the early universe, these constants had slightly different values, affecting how hydrogen interacted with radiation. If this were true, it would mean that our entire understanding of physics is based on a framework that is only an approximation of reality. Some scientists have even proposed that this anomaly could hint at the presence of extra dimensions, hidden layers of reality beyond the three-dimensional space we experience. If such dimensions exist, they could have influenced the behavior of matter in the early universe, leading to the unexpected 21 centimeters signal we see today. But the only way to know for sure is to gather more data. That's why researchers around the world are building more advanced radio telescopes, designed to scan the sky with unprecedented precision. The Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SKA, are two of the most ambitious projects aimed at detecting and analyzing the 21 centimeters hydrogen signal in even greater detail. If they confirm the EDGE's findings, then we'll know we're on the verge of a major breakthrough in our understanding of the universe. If they don't, then the mystery only deepens. Was the EDGE's signal a mistake? Was there some interference we didn't account for? Or is the truth even stranger than we imagined? This is what makes space mysteries so compelling. Every time we think we have the answers, the universe throws us a curveball. The redshifted 21 centimeters hydrogen line was supposed to be a simple, predictable tool for studying the early cosmos, but instead, it has become one of the biggest enigmas in modern astrophysics. And that's why we keep looking. Because somewhere in the vastness of space, hidden in the faint echoes of the past, lies a truth waiting to be uncovered. A truth that could reshape our understanding of the universe itself. But if there's one thing history has shown us, it's that the universe rarely gives up its secrets easily. The redshifted 21 centimeters hydrogen anomaly isn't just another data point, it's a crack in the foundation of what we thought we understood about the early universe. And every crack has the potential to lead to something revolutionary. To fully grasp why this discovery is so important, let's dive deeper into the mechanics of the 21 centimeters hydrogen line itself. Hydrogen is the most abundant element in the universe, making up around 75% of all normal matter. And when a hydrogen atom's electron flips its spin state, it either absorbs or emits radio waves at exactly 21 centimeters. This process occurs naturally across the cosmos, but when the universe expands, it stretches these radio waves, shifting them into lower frequencies, a phenomenon known as redshifting. By studying how much the 21 centimeters signal is redshifted, we can determine how far back in time it originated. The more redshifted it is, the older the signal. Scientists expected to detect a faint but predictable signal from the neutral hydrogen that filled the universe before the first stars ignited. Instead, they found something that shouldn't be possible, a signal that suggested the hydrogen was significantly colder than our models predicted. To understand why this is such a big deal, we have to consider what was happening during the universe's so-called dark ages. After the Big Bang, the universe was filled with high-energy radiation that kept all matter in an ionized state, meaning electrons and protons couldn't combine to form neutral atoms. But as the universe expanded and cooled, these particles eventually recombined, creating neutral hydrogen. At this point, there were no stars, no galaxies, just a vast ocean of hydrogen gas stretching across the cosmos. During this time, the only sources of energy that could heat this gas were weak interactions with the cosmic microwave background, CMB, and potentially some exotic dark matter interactions. According to our models, the hydrogen should have been at a temperature of around 7 Kelvin. But the EDGE's experiment detected a signal that implied the hydrogen was even colder, closer to 3 Kelvin. That might not seem like a big difference, but in the realm of cosmology it's massive. A discrepancy like this suggests that something else was influencing the hydrogen. But what? One of the most popular theories is that dark matter played a role. Dark matter is thought to make up around 85% of the total matter in the universe, yet we still don't know what it is. If dark matter had even a weak interaction with normal hydrogen, it could have drained energy from it, cooling it further than expected. This would be groundbreaking because, up until now, dark matter has been assumed to interact only through gravity. If it has even the slightest electromagnetic or thermal interaction, it would open up entirely new avenues for research. Some models propose that dark matter could be made up of extremely lightweight particles that interact with normal matter through a new, undiscovered force. These particles could have absorbed energy from hydrogen, explaining the anomaly. If this theory holds up, it would be the first direct evidence that dark matter isn't completely invisible. It actually has some level of interaction with the rest of the universe. Another possible explanation involves exotic physics, such as interactions with axions, a hypothetical type of particle that could help explain dark matter. If axions exist, they could have affected the early hydrogen in ways we don't yet fully understand. Some theories suggest that axions could oscillate between different states, subtly influencing the way hydrogen absorbs and emits radiation. There's even a possibility that the anomaly is pointing toward a fundamental flaw in our understanding of how the universe evolved. What if the cosmic microwave background isn't as uniform as we thought? What if there were pockets of the early universe that cooled differently than others due to unknown processes? If that's the case, then our entire timeline of cosmic evolution might need to be revised. But before we get too carried away, there's always the chance that this anomaly is the result of an observational error. The EDGES experiment was incredibly precise, but radio astronomy is notoriously difficult. Earth's atmosphere, interference from human-made signals, and even subtle equipment imperfections could all introduce errors. That's why follow-up studies using more advanced radio telescopes, like the Square Kilometre Array, are so important. If they confirm the EDGES findings, then we know we're dealing with something real. If they don't, then we might have to rethink everything. Even if the anomaly turns out to be a measurement error, the pursuit of this mystery has already advanced our understanding of the early universe. It has forced scientists to reconsider long-held assumptions, explore new models of physics, and push the boundaries of what's possible in radio astronomy. That's the beauty of space mysteries. They challenge us to think bigger, to question everything we thought we knew, and to keep searching for answers. The search for the truth behind the redshifted 21 cm hydrogen line is far from over. In the coming years, new telescopes, more precise observations, and deeper theoretical studies will bring us closer to unlocking its secrets. Whether it leads us to dark matter interactions, new physics, or an entirely different understanding of the universe, one thing is certain: we are on the edge of a discovery that could change everything. And that's the true power of the cosmos. It never stops surprising us. But what if the implications of this anomaly go even further than we imagine? What if this isn't just about dark matter or an unexplored interaction in physics? What if the redshifted 21 cm hydrogen line is pointing towards something even more fundamental? Something that challenges the very nature of the universe itself? Let's entertain a radical idea for a moment. What if the reason the hydrogen appears colder than expected isn't due to dark matter or exotic particles, but because the early universe wasn't behaving the way we thought? We assume that the laws of physics have been constant since the Big Bang, but what if they weren't? What if, in the early universe, the laws that govern energy transfer, particle interactions, or even time itself were slightly different? This is a concept that physicists have been quietly exploring for years. The possibility that the fundamental constants of nature might not be as constant as we assume. Things like the fine structure constant, which determines the strength of electromagnetic interactions, or the gravitational constant, which dictates the force of gravity, are assumed to be fixed. But some theories suggest that these values might have shifted ever so slightly in the early universe. If this is true, it could explain why the 21 cm hydrogen line appears the way it does. A slight variation in these constants could mean that hydrogen atoms in the early universe emitted or absorbed radiation differently than we expect, leading to a cooler signal than our models predict. And if that's the case, then we might have just stumbled onto something truly paradigm-shifting, direct evidence that the very fabric of physics evolved over time. This idea is mind-blowing because it suggests that the universe itself might have had different rules in its infancy. Maybe the speed of light was slightly different. Maybe quantum mechanics behaved in a subtly different way. Maybe gravity was just a little weaker or stronger than it is today. If true, this would mean that our entire understanding of cosmology needs to be reworked from the ground up. But there's another possibility that's even stranger. What if the anomaly in the 21 cm hydrogen line is evidence of an interaction with another universe? Some theories in physics, particularly those involving the multiverse, suggest that our universe might not be alone. Instead, it could be just one of many universes, each with its own physical laws and properties. If our universe ever brushed against another universe in its early stages, the energy exchange could have affected the cooling of hydrogen in unexpected ways. Imagine two universes existing side by side, like bubbles in a vast cosmic ocean. If they interacted briefly, perhaps through a gravitational pull or an exchange of exotic particles, this could have influenced the way energy flowed in the early universe, altering the temperature of neutral hydrogen and producing the anomaly we see today. This might sound like pure speculation, but some physicists have been exploring mathematical models that suggest interuniversal interactions could leave behind detectable imprints. The redshifted 21 cm hydrogen anomaly might be the first tangible evidence that our universe isn't isolated, that it has, at some point, interacted with something beyond itself. Of course, these ideas are on the cutting edge of theoretical physics. We don't have enough data to confirm or deny them. But the fact that the 21 cm hydrogen anomaly exists at all means that something unexpected happened in the early universe. Whether it's dark matter interactions, new physics, shifting constants, or even a multiversal encounter, the mystery remains open. And that's what makes this so exciting. We are on the brink of discovering something that could completely rewrite our understanding of the cosmos. The coming years will be crucial, as new experiments and observations continue to refine our picture of the early universe. If follow-up studies confirm the anomaly, then we know we're onto something big. If they don't, then we'll have to dig even deeper, searching for explanations we haven't even considered yet. But one thing is certain, the universe still holds secrets we have yet to uncover. And as long as mysteries like this exist, the search for truth will never end. If this anomaly is real, if the redshifted 21 cm hydrogen signal is truly pointing to something beyond our current understanding, then we're standing at the edge of a scientific revolution. The question isn't just what caused it, but what else we might be missing. Because if one assumption about the early universe turns out to be wrong, how many others are also waiting to be overturned? Let's consider another possibility. Could this anomaly be hinting at the presence of an unknown form of energy? We already know that dark energy, the mysterious force driving the accelerated expansion of the universe, makes up nearly 70% of the cosmos. But what if there was another form of energy active in the early universe, one that we haven't accounted for? Some physicists have proposed the idea of an early universe. Fifth force. A fundamental interaction beyond gravity, electromagnetism, and the nuclear forces. If such a force existed, it could have affected how hydrogen cooled during the cosmic dark ages, leading to the unexpected signal we see today. This force might have only been relevant at extreme cosmic distances or under certain temperature conditions, which is why we don't observe it in modern physics experiments. But here's where things get even stranger. If an unknown force or energy field influenced the early universe, it might still exist today, hidden, undetected, operating in ways we haven't yet realized. What if the effects of this force are still subtly shaping cosmic structures, influencing the formation of galaxies, or even affecting the nature of space-time itself? The redshifted 21 cm hydrogen anomaly could be the first glimpse of a deeper layer of reality, a hidden aspect of the universe that we've never directly observed before. If that's true, then this discovery isn't just about the early universe. It's about unlocking an entirely new piece of physics. To understand the gravity of this, think about the way past anomalies in physics have led to revolutionary breakthroughs. The orbit of Mercury didn't match Newtonian predictions, until Einstein's general relativity explained it with curved spacetime. The ultraviolet catastrophe in blackbody radiation made no sense, until Planck's quantum mechanics changed everything. The redshifted 21 cm hydrogen line might be another moment like that, where a strange observation forces us to rethink everything we thought we knew. So how do we test these ideas? One way is through more precise observations of the 21 cm hydrogen signal across different regions of the sky. If the anomaly is real and not just a measurement error, it should appear consistently in different datasets. Scientists are already planning more detailed radio astronomy surveys to confirm the signal and map out how it varies across cosmic time. Another approach involves looking for indirect effects. If an unknown force or interaction caused this anomaly, it might have left fingerprints elsewhere, perhaps in the cosmic microwave background, the distribution of galaxies, or the behavior of dark matter itself. New experiments, including next-generation telescopes and particle physics studies, could help us find these hidden connections. But let's go even deeper. What if this isn't just about a new force or a new particle? What if it's about the nature of space-time itself? Some physicists have speculated that, in the earliest moments of the universe, space-time might not have behaved the way we expect. Instead of being a smooth, continuous fabric, it might have been more chaotic, perhaps even quantized at the smallest scales. If true, then the way hydrogen interacted with radiation back then might have been influenced by the very structure of space-time. Instead of absorbing and emitting energy in a predictable way, it could have behaved in ways we don't yet understand, leading to the strange temperature readings we see now. This ties into another deep mystery: quantum gravity. Right now, our two best theories, general relativity and quantum mechanics, don't fully agree with each other. We don't have a complete theory of how gravity works at the smallest scales. But if the 21 centimeters hydrogen anomaly is pointing towards something fundamental about how space-time behaved in the early universe, it could be a crucial clue in solving this puzzle. Imagine what that would mean. It wouldn't just change our understanding of the past, it would change our understanding of everything. It could lead to a new theory of physics, one that unifies gravity with quantum mechanics, explains the nature of dark matter and dark energy, and reveals hidden aspects of the universe we've never even considered. This is why the redshifted 21 centimeters hydrogen line is so much more than just an odd radio signal. It's a window into the deepest mysteries of the cosmos. Whether it turns out to be evidence of dark matter interactions, an unknown force, a shift in fundamental constants, or something even stranger, one thing is clear: the universe is still full of surprises. And perhaps the biggest mystery of all is this: what else is out there, waiting for us to discover? If the redshifted 21 centimeters hydrogen anomaly is truly revealing something deeper about the universe, then the implications go far beyond what we've already considered. It could mean that we've been looking at cosmology through the wrong lens this entire time. What if the anomaly is a sign that the early universe wasn't just expanding, but that something even more profound was happening, something that altered the very nature of reality itself? One possibility is that we're seeing evidence of a phase transition in the fabric of space-time. Just like water can change from ice to liquid to vapor depending on temperature and pressure, the universe itself might have undergone phase transitions in its earliest moments. These transitions could have affected how energy and matter behaved, influencing the way hydrogen interacted with radiation. Some theories suggest that in the first few 100 million years after the Big Bang, the fundamental forces of nature were not yet separate but were unified in a single force. As the universe cooled, this force might have broken into the four we recognize today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. If this process didn't unfold exactly as we assume, it could have left strange imprints on the cooling hydrogen, resulting in the unexpected signal we now see. But what if it's even weirder than that? What if the early universe wasn't just transitioning through different physical states, but was actually holographic in nature? There's a mind-bending theory in physics called the holographic principle, which suggests that the entire three-dimensional universe might be a projection from a deeper, two-dimensional reality. If the universe was behaving in a fundamentally different way during its early stages, perhaps governed by different rules, or even existing in fewer dimensions, then the way hydrogen atoms absorbed and emitted energy might have been completely different from what our current models predict. This could explain why the 21 centimeters hydrogen line appears cooler than expected, because the universe itself was playing by different rules back then. And here's where things take an even more dramatic turn. If the holographic principle applies to the early universe, could it still apply today? Could the reality we experience, the vast cosmos filled with galaxies, stars, and planets, be just a projection of something deeper? And if so, could this anomaly be the first clue that we're seeing behind the veil of reality itself? These ideas might sound extreme, but physics is no stranger to mind-blowing revelations. Quantum mechanics already tells us that particles can exist in multiple states at once, that entanglement allows information to travel instantly across vast distances, and that empty space is teeming with virtual particles popping in and out of existence. The universe has never conformed to human intuition. It has always been stranger than we could have imagined. So what do we do now? The first step is confirming the signal with even greater precision. Scientists are already working on new experiments, using more advanced radio telescopes to map out the redshifted 21 cm hydrogen line across different regions of space. If they detect the same anomaly in multiple independent datasets, then we know for sure that we've uncovered something real, something that demands an explanation. From there, physicists will begin testing different models. Does the anomaly fit better with a dark matter explanation, or with a new force? Does it suggest a change in fundamental constants, or is it pointing towards something even deeper? Could it be linked to other cosmic mysteries, like the unexplained cold spot in the cosmic microwave background, or the strange behavior of dark energy? We are at the beginning of what could be one of the most profound discoveries in the history of science. The redshifted 21 cm hydrogen anomaly might not just be a strange radio signal. It could be the key to unlocking secrets about the nature of reality itself. And if that's true, then we are on the verge of something truly revolutionary. What else is hiding in the depths of the cosmos, waiting for us to uncover? What other anomalies have we overlooked, simply because they didn't fit our expectations? The universe is speaking to us through signals like these, whispering its secrets across billions of years of cosmic history. The only question is, are we ready to listen? If we are truly ready to listen, then we must push the boundaries of our current understanding and technology. The redshifted 21 cm hydrogen anomaly is not just a puzzle, it is a doorway to a deeper reality. But to step through that doorway, we need better tools, sharper minds, and the willingness to challenge everything we thought we knew. Right now, astronomers are preparing the next generation of radio telescopes that will scan the sky with unprecedented detail. One of the most promising projects is the Square Kilometre Array, SKA, a massive network of radio antennas being built in Australia and South Africa. Once operational, SKA will be able to detect faint radio signals from the very edge of the observable universe, allowing us to map out the early hydrogen distribution with unparalleled accuracy. If the anomaly is real, SKA should be able to confirm it beyond any doubt. But even that might not be enough. To fully understand what we are seeing, we may need a completely new kind of telescope, one that doesn't just observe radio waves, but also detects the subtle gravitational effects of cosmic structures. Gravitational wave observatories, like LIGO and Virgo, have already proven that we can listen to the ripples in spacetime caused by merging black holes and neutron stars. But what if we could use gravitational waves to probe the conditions of the early universe itself? Some researchers are exploring the idea that the 21 cm anomaly might be linked to primordial black holes, tiny black holes that could have formed in the first moments after the Big Bang. If these black holes interacted with hydrogen in unexpected ways, they might have left behind the strange signal we see today. Future gravitational wave detectors, like the proposed LISA, Laser Interferometer Space Antenna, could help us search for these ancient black holes and see if they played a role in shaping the universe. But even beyond technology, we need new physics to explain what's happening. Right now, our best model of the universe, known as lambda cold dark matter, lambda CDM, assumes that dark matter is a simple, non-interacting substance that only influences the universe through gravity. But what if that's wrong? What if dark matter has interactions we haven't accounted for? Perhaps even its own version of electromagnetic forces that affected the cooling of hydrogen in the early universe. Some physicists have proposed the idea of a dark sector, a hidden world of particles and forces that don't interact with normal matter in the way we expect. If dark matter has its own equivalent of photons, sometimes called dark photons, they could have transferred energy between normal hydrogen and the invisible dark matter field, altering its temperature and leading to the strange signal we see. If true, this would mean that dark matter is far more complex than we ever imagined. It wouldn't just be some inert, lifeless substance. It would be part of a shadow universe, with its own rules, interactions, and possibly even its own form of life. And that raises an even bigger question. If dark matter has its own hidden physics, could it also have structures? Could it form galaxies, planets, or even civilizations that are completely undetectable to us? Right now, we assume that life can only exist in the form we understand, made of atoms, interacting through normal forces like electromagnetism. But what if the universe is home to dark life, creatures that exist in a hidden realm, shaped by forces we cannot see? This might sound like science fiction, but remember, before we discovered exoplanets, many scientists thought that other planetary systems might be rare. Before quantum mechanics, no one believed that particles could be in two places at once. The history of science is filled with discoveries that once seemed impossible. And maybe the redshifted 21 cm hydrogen anomaly is the first step toward the next great discovery, the one that will show us that the universe is far more bizarre, far more intricate, and far more alive than we ever imagined. So we are left with a choice. Do we dismiss this signal as an error, as some anomaly that will eventually be explained away? Or do we embrace the possibility that we are standing on the edge of something groundbreaking? Do we dare to follow the clues wherever they may lead, even if they take us beyond the limits of known physics? Because if we do, we might just uncover the deepest secrets of the cosmos. And in doing so, we may finally understand what kind of universe we truly live in. If we are truly on the edge of a paradigm shift, then every assumption we've made about the universe must be reconsidered. The redshifted 21 cm hydrogen anomaly is not just an isolated mystery. It could be the first real crack in the foundation of modern cosmology. And if we look closely enough, we might find that the entire structure of our understanding is due for a major rewrite. Let's take a step back and ask a fundamental question. What if the early universe didn't behave the way we think it did? Right now, we assume that the first 400 million years after the Big Bang followed a predictable sequence. The universe expanded, cooled, and gradually formed the first structures. Hydrogen gas, which once existed as a vast, neutral sea, slowly clumped together due to gravity, igniting the first stars and galaxies. This process, called cosmic reionization, is thought to have reshaped the universe as ultraviolet light from these early stars ionized the surrounding gas. But what if that timeline is wrong? What if the hydrogen in the early universe was interacting with something we've never accounted for, something that changed the way it absorbed and emitted energy? Some researchers believe that sterile neutrinos, hypothetical particles that do not interact with normal matter except through gravity, could have played a role. If sterile neutrinos existed in large numbers, they could have provided a hidden form of radiation pressure that affected how hydrogen gas evolved. This would mean that our understanding of the universe's structure formation is missing a key ingredient. But that's only one possibility. There's also the idea that the vacuum of space itself was different in the past. The vacuum energy of the universe, sometimes called dark energy, is a mysterious force driving the accelerated expansion of the cosmos. But what if dark energy has not been constant over time? Some theories suggest that in the early universe, the vacuum had different properties, perhaps even allowing interactions between normal matter and something we can no longer detect today. If true, this could explain why the 21 cm hydrogen line is behaving unexpectedly. Maybe hydrogen was responding to forces that have since disappeared, leaving behind only this faint, redshifted whisper of a lost era. And here's where things get even stranger. What if the hydrogen anomaly is a sign that our universe is not alone? There's a concept in physics known as the multiverse hypothesis, the idea that our universe is just one of many, each with its own set of physical laws. Some versions of this theory suggest that new universes can bud off from existing ones, like bubbles forming in a vast cosmic foam. If this is true, then perhaps the strange 21 cm hydrogen signal is evidence of an ancient interaction between our universe and another. Imagine, for a moment, that in the first few 100 million years after the Big Bang, our cosmos briefly overlapped with a neighboring universe. If that universe had different physical constants, such as a slightly different speed of light, a different strength of gravity, or even a different form of dark matter, it could have temporarily affected the hydrogen in our universe. If we could prove this, it would be the first experimental evidence that the multiverse is real. But how would we even test such a hypothesis? One idea is to look for anisotropies, subtle patterns in the cosmic microwave background that don't match the standard model. If our universe had interacted with another in the past, there might be faint imprints of that interaction scattered across the sky. Future missions, like the proposed CMBS-4, Cosmic Microwave Background Stage 4, experiment, could provide higher resolution data to search for these clues. Another approach is to look for unexpected gravitational effects in the early universe. If a collision between universes did occur, it might have left behind gravitational waves, ripples in spacetime that could still be detectable today. Upcoming gravitational wave detectors, such as Einstein Telescope and Cosmic Explorer, could offer new ways to probe this possibility. And then, there's the most radical possibility of all. What if the hydrogen anomaly isn't just a relic of the past, but a message? What if we're not the first to study this strange signal? What if, in the deep history of the cosmos, another intelligence, one far older than humanity, also discovered this anomaly and left behind something for us to find? Right now, the search for extraterrestrial intelligence, SETI, focuses mostly on radio signals from nearby stars. But what if advanced civilizations communicate in ways we haven't even considered? Some researchers have speculated that an ancient civilization could manipulate fundamental cosmic signals, like the 21 centimeters hydrogen line, to encode information on a universal scale. If that's true, then the signal we're seeing might not just be a scientific anomaly. It might be a deliberate artifact, a message written into the structure of the cosmos itself. And if that's the case, then the biggest question of all is, what is it trying to tell us? If the redshifted 21 centimeters hydrogen line is more than just a scientific anomaly, if it is a message, an artifact, or even a warning, then we are faced with one of the most profound questions in human history. Who or what could have left it behind? Right now, we assume that intelligent life, if it exists elsewhere, would be bound by the same limitations we are. They would evolve on planets, communicate through electromagnetic signals, and leave behind physical traces of their existence. But what if intelligence in the universe is far older, far stranger, and far more deeply embedded in the fabric of reality than we ever imagined? Some scientists have speculated about the existence of cosmic-scale civilizations, intelligences that don't just inhabit planets, but manipulate entire galaxies. These hypothetical beings, sometimes referred to as Type 3 civilizations on the Kardashev scale, would have the ability to harness the energy of stars, control cosmic structures, and perhaps even alter the physics of the universe itself. If such a civilization once existed, perhaps billions of years ago, what traces would they leave behind? Would they build megastructures? Would they encode messages in the cosmic microwave background? Or would they leave behind something even more subtle? Something woven into the fundamental behavior of hydrogen, the most abundant element in the universe? If an ancient intelligence had the ability to manipulate hydrogen at a quantum level, they could have deliberately altered the way it absorbs and emits energy. The result? A signal that would remain imprinted in the universe for billions of years, long after the civilization itself had disappeared. And if this is the case, then the redshifted 21 centimeters anomaly isn't just an accident. It's a marker, a signpost left behind by something that wanted to be found. But found by whom? Here's where things take an even stranger turn. What if the message was never meant for us at all? Consider this: the universe is 13.8 billion years old. The first intelligent civilizations, if they emerged early, could have existed billions of years before Earth even formed. If they left behind signals, they may not have been intended for primitive species like us. Instead, they could have been left as a form of cosmic communication, a beacon meant for other advanced civilizations that would one day reach a certain level of understanding. If true, This would mean we have stumbled upon something far beyond our own comprehension. We are eavesdropping on a conversation that began long before we arrived, a conversation between civilizations so advanced that they no longer use technology in the way we do. Instead, they use the laws of physics themselves as their medium of communication. And if that's the case, then the biggest question isn't just what the message says. The biggest question is whether we are even capable of understanding it. If an ancient intelligence altered the behavior of hydrogen to create a cosmic signal, then our current scientific models are not just incomplete, they are fundamentally flawed. We are missing something crucial, something that goes beyond dark matter, beyond the Big Bang, beyond even our understanding of physics itself. Could it be that the fundamental laws of nature are not as fixed as we believe? Could an advanced civilization have rewritten parts of the universe's underlying code? This might sound like speculation, but there are serious scientific discussions about whether the laws of physics have changed over time. Some researchers suggest that the fine structure constant, a fundamental number governing the strength of electromagnetic interactions, may have been different in the early universe. If this is true, then the physics we observe today is only a snapshot of a larger, evolving system, one that may have been influenced by forces we do not yet understand. And if this is the case, then the redshifted 21 centimeters anomaly could be the first real clue that we are not alone, not just in space, but in the very structure of reality itself. So, what do we do now? The answer is simple: we keep looking. We refine our observations, build better telescopes, and push the boundaries of our theories. If there is a message hidden in the hydrogen of the cosmos, then we owe it to ourselves, and to whatever left it behind, to decode it. Because if we succeed, we may not just solve one of the greatest mysteries in astronomy. We may finally take our first step into a larger universe, one that has been waiting for us all along. The quest to uncover the truth behind the redshifted 21 centimeters hydrogen anomaly is more than just a scientific investigation. It's a journey into the heart of the universe itself, challenging everything we think we know about space, time, and the very nature of reality. The implications of this discovery stretch far beyond the realms of physics, cosmology, and astronomy. It forces us to confront the possibility that the universe may be far more complex, and far more mysterious, than we ever imagined. But as we continue this search, it's important to remember that what we're looking for is not just a singular answer, but a deeper understanding of our place in the cosmos. If the signal from neutral hydrogen does indeed hold the keys to the earliest structures of the universe, then it might also reveal something fundamental about our own origins. What does it mean for humanity if we discover that the universe is not just a random collection of matter, but a vast, interconnected network with its own purpose, rules, and perhaps even intelligence embedded within it? Could it be that we are merely the latest in a long line of civilizations that have risen, fallen, and left their traces behind in the cosmic fabric? Or are we truly unique, with a destiny shaped by forces yet to be fully understood? While we are still in the early stages of this investigation, one thing is clear. The search for the truth behind the redshifted 21 centimeters hydrogen line is about more than just understanding hydrogen. It is about looking deeper into the past, into the very origins of the universe, and possibly uncovering the profound secrets that lie hidden beneath the surface. Perhaps the most compelling part of this puzzle is the nature of the signal itself. As we've discussed, the redshifted 21 centimeters hydrogen line represents the faintest trace of ancient hydrogen gas, a remnant from the early universe that continues to carry its story across time. The fact that this signal has managed to persist for over 13 billion years, undetected until now, speaks to the scale of the universe's complexity. It is almost as if the universe has been whispering to us all along, waiting for us to listen. But what are we actually hearing? For all our technological advances, we are still barely scratching the surface of the universe's true nature. With each new discovery, we realize that the universe is full of hidden layers, each one more mysterious than the last. And it's not just about uncovering the past, but understanding how these hidden layers influence the present. For instance, how does the early universe's hydrogen gas relate to the cosmic structures we observe today? And how do these interactions impact the ongoing expansion of the universe itself? The redshifted 21 cm hydrogen line could hold the answer to these questions. But to fully unlock its secrets, we need to push the boundaries of our understanding in ways we've never done before. That means using the most advanced telescopes and instruments at our disposal, developing new theories to explain what we're observing, and most importantly, remaining open to the possibility that the universe may not operate according to the rules we know. One of the biggest hurdles in this journey is the question of how to observe this faint signal. The 21 cm hydrogen line is incredibly weak, and its detection requires extremely sensitive equipment. In recent years, scientists have made strides with low-frequency radio telescopes such as the SKA, Square Kilometer Array, and HERA, Hydrogen Epoch of Reionization Array, both of which aim to observe the earliest stages of the universe's development by detecting the faint emissions from neutral hydrogen gas. These instruments are designed to capture radio waves at frequencies where the 21 cm line lies, providing a direct view into the distant past. But even with these cutting-edge technologies, the signal remains elusive. The challenge is not just about detecting the hydrogen emissions themselves but also about distinguishing them from the vast amount of background noise that fills the universe. Cosmic radiation, other radio signals, and even interference from Earth's atmosphere can obscure the faint 21 cm signal, making it difficult to isolate and study. This is where the mystery deepens. Despite all the advancements in radio astronomy, the fact that we've yet to detect the signal in its full clarity raises the question: is the signal we are searching for even what we think it is? Could it be that the 21 cm line is only a fragment of something much larger, an echo of events that occurred long before hydrogen ever formed? Or perhaps it's not a signal at all, but rather a manifestation of some other cosmic phenomenon that we have yet to identify? These questions, though daunting, are the very reason why we cannot afford to stop searching. Each unanswered question only leads to more possibilities, and every step forward brings us closer to the answers we seek. The quest for the redshifted 21 cm hydrogen line is, in many ways, a journey not just through space, but through time itself. As we look to the future of this exploration, we can only imagine the breakthroughs that await. The discovery of the redshifted 21 cm hydrogen line in its entirety could have profound implications for our understanding of the universe. It could rewrite the history of the early cosmos and provide clues about the formation of the first galaxies and stars. It could reveal new insights into the role of dark matter and dark energy, forces that we still don't fully understand. And it could open up new avenues of research into the very fabric of space-time itself. But the search for this elusive signal is not just about answering scientific questions. It's also about expanding our perspective as a species. For millennia, humanity has looked up at the stars, wondering if we are alone in the universe. With every new discovery, we get a little closer to the truth. The redshifted 21 cm hydrogen line might be the key to answering that question once and for all. Or perhaps, as we've suggested, it's just the beginning of a much larger mystery, one that stretches beyond the limits of our current understanding. The redshifted 21 cm hydrogen line might be more than just a signal from the past. It could be a reminder that the universe is far larger, far older, and far more mysterious than we can even begin to comprehend. And perhaps, just perhaps, it's calling us to look deeper, to reach further, and to think in ways we never thought possible. The pursuit of the 21 cm hydrogen signal transcends the boundaries of conventional astronomy. It presents an exciting frontier not only for scientists but also for all of humanity. It forces us to confront the vastness of time and space and our own place within that immense cosmos. What we discover through this signal may not just change our scientific knowledge, it could reshape the philosophical way we think about existence itself. What are we, if not a tiny speck in the infinite stretch of time and space? Yet, here we are, reaching out to the universe, trying to piece together the narrative of how everything came to be. The mysteries of the 21 cm hydrogen line have already begun to redefine our understanding of the early universe. As we delve deeper into these questions, it's clear that there is a significant gap in our knowledge about the state of the universe before the first stars ignited. This is a crucial period in cosmic history, often referred to as the cosmic dark ages. It is a time when the universe was filled with neutral hydrogen gas, a time before light could freely travel through space, a time when the first stars and galaxies had yet to form. This is where the 21 centimeters hydrogen line comes into play. The signal, emitted by neutral hydrogen, holds the potential to give us a window into this cosmic dark age, providing an unprecedented view of the conditions that existed just after the Big Bang. The faint emission from hydrogen in this period, if detected clearly, could allow us to map out the structure and evolution of the universe before the formation of stars. It could help us understand how the first galaxies were born and how the process of reionization, the event that made the universe transparent to light, took place. Yet, despite its significance, detecting this signal has been a monumental challenge. The 21 centimeters hydrogen line is not like other cosmic signals that we have detected in the past. The hydrogen itself is faint, its emission incredibly weak, and the signal is easily drowned out by the many sources of interference in space. To isolate it from all this noise, we need instruments of unprecedented sensitivity. Enter the cutting-edge technology that has been developed to tackle this very challenge. The Square Kilometer Array, SKA, is one such instrument that is poised to play a pivotal role in this search. It is designed to detect the faintest radio waves from across the universe. With its vast array of antennas, SKA will be able to capture low-frequency signals, exactly the type of signals we expect from the 21 centimeters hydrogen line. The SKA will also be able to detect these signals from regions of space that are far beyond our current reach, potentially unlocking new information about the universe's infancy. Alongside the SKA, we have other instruments like HERA, Hydrogen Epoch of Reionization Array, a smaller but equally important radio telescope array. HERA's primary goal is to detect the 21 centimeters line in its entirety by focusing on the epoch of reionization, a period when hydrogen gas was first ionized by the first stars. These observatories and others are part of an effort to explore the very earliest stages of the universe, an endeavor that could have profound implications for cosmology. But these efforts also bring with them a set of challenges. The signal we are searching for is not just faint, it is also buried under layers of interference. One major obstacle is the cosmic microwave background, CMB, the afterglow of the Big Bang, which permeates all of space. The CMB emits its own radiation that can mask the signal from the 21 centimeters line. This has made it exceedingly difficult for astronomers to isolate the hydrogen signal from the rest of the cosmic noise. Additionally, the Earth's atmosphere and artificial radio signals further complicate the task. To counteract these challenges, researchers must design instruments that can precisely filter out unwanted noise while amplifying the faint signal of the 21 centimeters hydrogen line. These obstacles, however, are not stopping scientists from moving forward. Every breakthrough brings us closer to a clearer picture of the early universe. And it's not just about detecting the signal. It's about understanding what the signal represents. What can we learn from this faint whisper of the cosmos? How can we use this information to understand the processes that shape the universe as we see it today? There's another fascinating aspect of the 21 centimeters hydrogen line. It offers a unique opportunity to probe the distribution of dark matter. One of the greatest mysteries in modern cosmology is the nature of dark matter. This invisible substance makes up a significant portion of the universe's mass, yet we still know very little about it. The 21 centimeters line could provide clues about the way dark matter interacts with normal matter, especially in the early universe. This is because the neutral hydrogen gas that emits the 21 centimeters signal interacts with dark matter in ways that we are only beginning to understand. By studying this interaction, we might gain insights into the properties of dark matter, which could lead to groundbreaking discoveries. The exploration of the 21 centimeters hydrogen line is not just about understanding the early universe. It's also about exploring the possibilities of what lies beyond the limits of our current knowledge. Could there be other, as yet undetected, signals hiding in the vast expanse of space? Could the universe be full of whispers and echoes, waiting for us to discover them? The more we listen to the cosmos, the more we realize that we are just beginning to scratch the surface. Each signal, each discovery, brings with it new questions and new possibilities. As we look toward the future, the prospects of discovering the redshifted 21 cm hydrogen line in full detail are tantalizing. If we are successful in detecting it, we will be able to trace the earliest structures of the universe with unprecedented precision. We may be able to create detailed maps of the first galaxies, explore the processes that led to the formation of the first stars, and ultimately uncover the history of the universe from a time when it was still in its infancy. But more than that, the discovery of this signal will be a monumental achievement in human exploration, a testament to our relentless pursuit of knowledge and our deep curiosity about the universe we inhabit. It will serve as a reminder that the quest for understanding is never complete. Each new discovery opens the door to more mysteries, more questions, and more opportunities for exploration. The mystery of the redshifted 21 cm hydrogen line is one that has captivated scientists for years, and it will continue to captivate generations to come. As we continue to search for this elusive signal, we are reminded that we are part of something much larger than ourselves. The universe is vast, complex, and full of hidden secrets, but with every step forward, we get closer to understanding its true nature. And perhaps, that is what this search is truly about, not just uncovering the mysteries of the cosmos, but uncovering our place within it. As we peer into the depths of space, we are not only looking outward, we are also looking inward, searching for meaning, for connection, and for a deeper understanding of the forces that shape our existence. As our technological advancements push the boundaries of what is possible, the 21 cm hydrogen line stands as a prime example of how our curiosity drives innovation. The idea of using radio waves to understand the universe's earliest moments might seem like something out of a science fiction novel, but today it is becoming a reality. The challenge of detecting the redshifted 21 cm signal lies not just in the faintness of the emission, but in the intricacies of how we need to interpret it. The radio waves emitted by the hydrogen atoms in the early universe are stretched due to the expansion of space. This stretching causes the wavelengths of the 21 cm signal to be redshifted. The term, redshift, referring to the phenomenon where light, or radio waves, moves towards the longer wavelengths as the universe expands. The further back we look in time, the more redshifted the signal becomes. This means that we need to look deeper into space to study the more distant and ancient hydrogen clouds. But as we have already discussed, the farther we look, the harder it becomes to isolate the faint signal from the noise of the cosmos. One of the techniques that astronomers use to isolate the 21 cm signal from the noise is known as cross-correlation. By comparing the signals from different parts of the sky and measuring their relationship, scientists can filter out the extraneous noise and hone in on the faint signals of interest. This approach is akin to the method used by detectives piecing together fragments of evidence to solve a mystery. Cross-correlation allows astronomers to enhance the signal of the hydrogen gas and reduce the interference from other sources, such as the cosmic microwave background. One of the biggest breakthroughs in this area has come from the increasing sensitivity of radio telescopes. Instruments like the Low-Frequency Array, LOFAR, in the Netherlands and Murchison Wide Field Array, MWA, in Australia are designed to detect signals in the low-frequency radio spectrum, which is where the 21 cm signal resides. These telescopes, in combination with the efforts of observatories like SKA and Hera, are pushing the limits of what is possible in radio astronomy. The more sensitive we become to these signals, the more likely it is that we'll be able to discern the faint 21 cm line from the surrounding noise. But the quest to detect the 21 cm hydrogen signal isn't just about improving our instruments. It also requires improving our theoretical models. Understanding how hydrogen behaves in the early universe and how it interacted with other cosmic elements is critical for interpreting the data. For example, we need to account for the effects of cosmic reionization, the process by which the first stars and galaxies formed and began emitting ultraviolet light. This light ionized the surrounding hydrogen gas, transforming it from a neutral state into ionized protons and electrons. The precise timing and nature of reionization is a crucial piece of the puzzle, as it affects the 21 cm signal strength and redshift. Reionization is a critical phase in the evolution of the universe. Before this period, the universe was opaque to light, and only the faint glow of the hydrogen signal could be seen. After reionization, the universe became transparent, allowing light to travel freely through space. This transition marked the birth of the first stars and galaxies, and studying the 21 centimeter signal will help us trace the moment when this cosmic transformation took place. In a sense, the 21 centimeter signal serves as a cosmic fingerprint, providing clues about the processes that occurred in the early universe, before galaxies, stars, and planets took shape. But even as we refine our models and develop more advanced telescopes, there's still much we don't know about how the universe evolved during this time. For instance, we don't yet know exactly how long the epoch of reionization lasted, nor do we fully understand the role that the first galaxies played in the process. Did the first stars form in isolation, or did they coalesce into larger, more complex structures? Was the ionization process uniform across the universe, or did it occur in fits and starts? These are questions that we hope to answer by studying the 21 centimeters hydrogen line. There's also the fascinating question of whether or not we'll discover anything entirely unexpected along the way. Given the state of our knowledge, there's always the possibility that we will find anomalies in the data that don't fit our existing theories. These anomalies could potentially point to new physics, undiscovered properties of matter or forces that we've never before considered. For example, some researchers speculate that the 21 centimeters line could hold clues about exotic dark matter interactions. If certain types of dark matter particles interact with hydrogen gas in unexpected ways, this could cause deviations in the expected signal, potentially providing us with new insights into the nature of dark matter itself. Another intriguing possibility is that studying the 21 centimeter signal could help us detect cosmic strings, hypothetical, one-dimensional defects in spacetime that may have formed during the early universe. Cosmic strings are predicted to emit distinctive signals, and their interactions with hydrogen could, in theory, leave an imprint on the 21 centimeters line. Although there's no direct evidence for cosmic strings as of yet, their potential existence represents one of the many mysteries that scientists hope to explore by studying the hydrogen signal. These possibilities are why the search for the 21 centimeters hydrogen line is so important. It's not just about piecing together the history of the universe. It's about searching for hidden answers that might not fit into our current models of physics, but could open up entirely new areas of discovery. What excites scientists and astronomers the most is the idea that this signal might provide us with a snapshot of the universe at its earliest moments. Imagine being able to see not just the first galaxies, but the very formation of the large-scale structures that make up the universe today. With each breakthrough, we could unlock more detailed maps of these early structures, which could help us better understand how the universe grew from a featureless, homogeneous gas into the rich and complex cosmos we observe today. Furthermore, the study of the 21 centimeters hydrogen signal has implications beyond just our understanding of the universe's evolution. The techniques and technologies developed to capture and analyze these faint signals have far-reaching applications in other fields of science and engineering. By developing more sensitive instruments and improving our ability to filter out noise, we are also advancing the fields of radio astronomy, signal processing, and even medical imaging. The process of isolating weak signals in noisy environments is a challenge shared by many disciplines, and the advancements we make in this area will undoubtedly have benefits beyond the realm of cosmology. The redshifted 21 centimeters hydrogen line is not just an exciting frontier in the field of astronomy, it is a frontier in human knowledge itself. As we continue to push the limits of what is possible, the discoveries we make will not only reshape our understanding of the universe but also challenge our perceptions of reality. It's an ongoing mystery that continues to fascinate and inspire scientists and dreamers alike. Each new piece of data we gather brings us closer to unlocking the secrets of the cosmos, revealing a universe more intricate and fascinating than we could have ever imagined. The search for the 21 centimeters hydrogen line is not just about finding answers. It's about expanding the scope of what we know, questioning our assumptions, and opening up new avenues for discovery. So, as we continue to look up at the stars, we do so with the knowledge that the universe is full of untold mysteries, just waiting to be uncovered. The redshifted 21 centimeters hydrogen line is one of the many keys that will unlock those mysteries, And with each new piece of data, we move closer to understanding the vast, cosmic story that is unfolding before us. The journey to uncover the secrets of the redshifted 21 cm hydrogen line is far from simple, and it challenges not only our technical abilities but our understanding of the universe itself. The complexities involved in detecting and interpreting this faint signal demonstrate the incredible hurdles that scientists must overcome to reach new frontiers in space exploration. As technology advances, so too does our capacity to probe the depths of space, and with each leap forward, we find ourselves peering into a cosmos that remains mostly hidden from our view. But what makes the 21 cm hydrogen line so tantalizing? To answer that, we must understand its place in the grand cosmic timeline. The 21 cm line corresponds to a specific frequency of radio waves emitted by neutral hydrogen atoms. In the early universe, these hydrogen atoms were a dominant form of matter, present in enormous quantities. The signal we detect today corresponds to hydrogen in its neutral state before it was ionized by the first stars. This period is known as the cosmic dawn, which marks the time when the universe began to evolve from a mostly featureless fog of hydrogen into the structured cosmos we see today. The importance of the 21 cm signal is that it acts like a cosmic map, allowing scientists to trace the changes in the state of the universe as it transitioned from darkness to light. It holds the potential to reveal the first moments of star formation, the growth of the earliest galaxies, and the process of reionization. This is the period that lies beyond the cosmic microwave background (CMB), the afterglow of the Big Bang, which gives us a glimpse into the universe's infancy. But the 21 cm hydrogen line allows us to peer even further into the distant past, into a time when the universe was undergoing drastic transformation. As we investigate these distant signals, we find that the 21 cm line doesn't just provide us with a map of the early universe, it tells a story. This story is one of growth, expansion, and evolution, and it helps to answer fundamental questions about how the first structures in the universe formed. How did the first galaxies arise from the primordial soup of gas? How did stars first ignite and begin to influence their surroundings? What caused the reionization of hydrogen, and how did it impact the cosmos as a whole? Every discovery we make about this line of hydrogen serves as a piece of the puzzle, slowly constructing a picture of the early universe. But much like piecing together the fragments of a long-lost manuscript, there are still many gaps in our understanding. For every new discovery, there are more questions that arise, fueling the curiosity that drives the quest to understand the universe. The more we learn, the more we realize that this story is far more complex and intricate than we could have ever imagined. Another key aspect of studying the 21 cm hydrogen line is its potential to unlock the mysteries surrounding dark matter and dark energy. These two enigmatic substances make up most of the universe's mass and energy, yet they remain largely undetectable by conventional means. Some researchers believe that studying the 21 cm line might provide insights into the properties of dark matter, particularly in how it interacts with regular matter. Since hydrogen was the primary element in the early universe, and since dark matter is thought to interact very weakly with ordinary matter, it's possible that there are subtle interactions between dark matter and hydrogen that could leave detectable traces in the 21 cm signal. If we are able to detect such traces, it could mark one of the most significant breakthroughs in cosmology, offering us our first direct clues about the nature of dark matter. Furthermore, the 21 cm signal has the potential to reveal the existence of phenomena such as cosmic bubbles, regions where the hydrogen gas was ionized due to the formation of the first stars. These bubbles would leave a distinct imprint on the 21 cm signal, allowing scientists to study how the first stars and galaxies interacted with their environment. By mapping out these bubbles, astronomers could determine the exact timing and nature of cosmic reionization, helping to clarify how the first luminous objects transformed the early universe. The challenge, however, lies in the vastness and complexity of space. Even with advanced telescopes and sophisticated detection methods, isolating the 21 cm signal from the overwhelming background noise is no small feat. Space is full of interference, from emissions of gas and dust in our galaxy to cosmic microwave radiation from the Big Bang. Distinguishing the 21 centimeter signal from all of this noise requires an incredible amount of precision and ingenuity. One of the ways that scientists are overcoming these challenges is by building interferometers, large arrays of radio telescopes that work together to collect data. Interferometers use a technique called interferometry, where signals from multiple telescopes are combined to create a much larger effective telescope. This increases the sensitivity of the system, allowing it to detect extremely faint signals, like the redshifted 21 centimeters line. Projects like the Square Kilometre Array, SKA, a massive radio telescope being constructed in both Australia and South Africa, are set to revolutionize our ability to study the 21 centimeters line. With thousands of antennas working in tandem, the SKA will be able to collect data from vast regions of space, providing an unprecedented level of detail about the early universe. But the work doesn't stop there. The data collected by these telescopes must then be carefully analyzed to extract the meaningful information hidden within it. This is where the intersection of astronomy, physics, and data science comes into play. Scientists use complex algorithms to process the raw data, searching for patterns that can reveal insights about the early universe. With every breakthrough, we come closer to understanding the true nature of the cosmos, but there is still much more work to be done. The redshifted 21 centimeters hydrogen line isn't just a signal, it's a key that could unlock the most profound mysteries of the universe. Its discovery is a testament to the human drive for knowledge and our relentless pursuit of the unknown. As technology continues to improve and our understanding of the universe deepens, we may eventually find ourselves on the brink of new revelations that could change the way we think about space, time, and the very nature of existence itself. The quest to understand the 21 centimeters hydrogen line is more than just an academic pursuit. It is a journey of discovery that could help us understand our place in the vast cosmos. It challenges us to look beyond our immediate surroundings and to question everything we know about the universe. And as we look further and deeper into the cosmos, we are reminded that even the faintest signals can carry the weight of unimaginable knowledge. The excitement surrounding the 21 centimeters hydrogen line doesn't just come from its promise to reveal the earliest moments of the universe. It also stems from the broader implications for cosmology and the potential to redefine many of the current models we use to understand the cosmos. For instance, the study of this radio signal could refine our current theories about the formation and evolution of galaxies. We often think of galaxies as being born in a specific, orderly manner, but the 21 centimeter signal could reveal a much messier process, with galaxies emerging at different times and under varied conditions across the universe. One intriguing area where the 21 centimeters hydrogen line is expected to make a profound impact is our understanding of cosmic inflation. Cosmic inflation is the theory that the universe underwent an incredibly rapid expansion during the first moments after the Big Bang, stretching space-time by an enormous factor in an infinitesimal fraction of a second. This theory helps explain many of the observed features of the universe, such as its large-scale structure and uniformity. However, inflation is still somewhat mysterious, and while we have indirect evidence of its existence, we have yet to directly observe its effects. By studying the 21 centimeters hydrogen line, scientists may uncover evidence of inflationary phenomena, perhaps in the form of subtle fluctuations in the signal that correlate with inflationary models. These findings could serve as a new window into the earliest moments of the universe, helping to validate or refine our understanding of cosmic inflation and its role in shaping the universe as we know it. In addition to understanding the early universe, the 21 centimeters hydrogen line is providing insights into the large-scale structure of the universe. This structure is essentially the cosmic web, where galaxies and clusters of galaxies form intricate patterns throughout space, much like a vast network of interconnected nodes. The way that hydrogen is distributed and behaves in the early universe can tell us a lot about how this cosmic web evolved. By mapping out the distribution of hydrogen through the 21 centimeters signal, we can trace the growth of these large-scale structures and better understand the forces that shape them. We might even uncover new types of cosmic objects, or phenomena that have thus far remained undetected. In exploring the early universe, the 21 centimeters hydrogen line isn't just a tool for scientists. It's a bridge to a completely new realm of discovery. It's as if we've been given a glimpse into a hidden chapter of the universe's story, a chapter that was previously obscured from view by the limits of our observational tools. As we gather more data and refine our techniques, we move closer to unraveling the most fundamental questions. What happened in the earliest moments after the Big Bang? How did the universe evolve from a featureless fog to the rich, complex tapestry we see today? But these questions are just the beginning. The 21 cm hydrogen line is also an invaluable resource for studying the larger cosmic forces at play, forces that operate on scales far beyond our current understanding. One such force is dark energy, the mysterious force driving the accelerated expansion of the universe. While much progress has been made in understanding dark energy through the study of distant galaxies and supernovae, there is still much to learn. If the 21 cm hydrogen line can help us understand the distribution of matter and energy in the early universe, it might also provide a new way of studying the effects of dark energy. For example, subtle shifts in the 21 cm signal could offer clues about how dark energy influenced the expansion of the universe during critical moments in its history. On the flip side, the 21 cm hydrogen line is not only essential for understanding the universe's birth, but it can also help scientists explore its eventual fate. Understanding the processes of reionization and the cooling of hydrogen can provide clues to the long-term evolution of the universe. As stars age and galaxies evolve, the universe will continue to expand and change, and the hydrogen gas that filled the cosmos will evolve as well. By tracing how the hydrogen gas has behaved throughout the history of the universe, we can extrapolate what might lie ahead in its future. This could give us new insights into the ultimate fate of the universe, whether it will continue to expand forever, slow down, or eventually collapse in on itself. The challenge, however, is that we are looking at a universe that is constantly evolving, and the faint signals we are trying to detect are being stretched and distorted by various factors, such as cosmological redshift. As light travels through space, it stretches out due to the expansion of the universe, meaning that even though the 21 cm line originates from hydrogen at a much earlier time, the signal we detect today is shifted into longer wavelengths. This means that studying the 21 cm hydrogen line requires incredible precision in both the detection and the interpretation of the signal. Even minor shifts in the signal can indicate massive changes in the universe's structure or its evolution. One approach that is being used to tackle this challenge involves building space-based radio telescopes. The atmosphere on Earth interferes with many of the signals we try to detect from space, particularly in the radio frequency spectrum, which is exactly where the 21 cm signal resides. The dense atmosphere of Earth absorbs much of the radio wave spectrum, making it difficult to study faint signals from the cosmos. By sending radio telescopes into space, like the proposed Lunar Radio Array or NASA's CubeSat missions, scientists hope to avoid the interference caused by the Earth's atmosphere and capture the 21 cm signal in its purest form. These space-based instruments could help create an unprecedented map of the early universe, free from the noise that plagues ground-based observations. Additionally, collaborations between different observatories and research institutions are critical in making significant strides in understanding the 21 cm hydrogen line. Projects like the Hydrogen Epoch of Reionization Array, HERA, and the Low Frequency Array, LOFAR, are part of global efforts to build massive networks of radio antennas that can work together to gather and analyze the 21 cm signal. These international collaborations enable scientists to pool their resources and share their findings, speeding up the process of discovery. The search for the 21 cm hydrogen line is a long and ongoing effort. The universe has been evolving for over 13 billion years, and we are just beginning to scratch the surface of its history. But every new breakthrough takes us one step closer to answering some of the most profound questions in science. What is the true nature of the early universe? How did galaxies form, and when did the first stars begin to shine? How did the universe evolve, and what secrets does it hold for the future? The redshifted 21 cm hydrogen line may hold the key to unlocking these mysteries, and many more. The journey of discovery is far from over, and with each new step, the cosmos reveals just a little bit more of its story. As we continue exploring the potential of the 21 centimeters hydrogen line, the sheer scale of what it could reveal becomes even more remarkable. Imagine being able to trace the formation of the very first galaxies and clusters of galaxies, right from the very beginnings of the universe. This is what the 21 centimeters hydrogen line is offering, a roadmap of the universe's evolution, drawn in the language of hydrogen. This hydrogen, which makes up the bulk of the matter in the universe, serves as a kind of universal marker that can guide us through the cosmos' grand history. The cosmic dawn is one of the most fascinating phases of the universe's early history, and the 21 centimeters signal holds the potential to illuminate this era like nothing else can. This is the period when the first stars began to form, breaking through the dense fog of neutral hydrogen that had filled the universe after the Big Bang. Prior to this, the universe was a dark, opaque place, with no sources of light. The first stars, however, began to emit ultraviolet radiation, which interacted with the hydrogen atoms, ionizing them and eventually leading to the epoch of reionization. By detecting the 21 centimeters signal from this era, we can study how the first stars and galaxies shaped the universe and paved the way for the more complex structures that followed. One of the most exciting aspects of the 21 centimeters hydrogen line is its ability to probe the unknowns of reionization. Reionization is the process by which the universe transitioned from a neutral state, dominated by hydrogen atoms, to the ionized state we observe today. Before the first stars and galaxies formed, the universe was a dark, nearly uniform fog of hydrogen and helium. When the first stars began to shine, their radiation broke apart the hydrogen atoms, ionizing them and creating the universe we see today. By studying the 21 centimeters signal from this period, scientists can pinpoint the exact timeline of reionization, and possibly uncover details about how the first stars and galaxies formed. It could also help us understand the sources of the energy that led to this ionization, whether it was due to massive stars, supermassive black holes, or some other unknown phenomena. The connection between the 21 centimeters hydrogen line and reionization is especially significant because reionization is one of the most critical periods in the history of the universe. It marks the shift from a universe that was dark and nearly featureless to one that was populated with stars and galaxies, the building blocks of everything we know today. Understanding reionization can help us piece together how the universe came to look the way it does and how it evolved over time. One of the most challenging aspects of studying the 21 centimeters signal is the enormous distances it must travel. The signal emitted by hydrogen during the early universe has traveled across the vast expanse of space for billions of years, stretching as the universe expanded. The farther back in time we look, the more the signal gets redshifted, shifting toward longer wavelengths. This redshift is a crucial clue that can tell us how much the universe has expanded since the signal was emitted. It's like using a stretch of rubber to measure the size of a balloon. The further back in time we look, the more the signal has been stretched out. This makes detecting the 21 centimeters signal from the early universe incredibly challenging, but it also means that when we finally do detect it, it will be one of the most profound discoveries in the history of cosmology. As we look even deeper into the potential of the 21 centimeters signal, there is the possibility of discovering new physics that we never anticipated. For instance, the signal could potentially reveal previously unknown forms of matter or energy, or it might indicate that our current models of physics need to be adjusted. It could even provide insight into the dark matter that makes up much of the universe's mass but has never been directly observed. Although dark matter doesn't interact with light in the same way normal matter does, it might influence the 21 centimeters hydrogen line in subtle ways, offering us clues about its properties and distribution. Furthermore, the 21 centimeters hydrogen line is not just a tool for looking at the early universe. It can also help us investigate the ongoing dynamics of the cosmos. For example, it can provide insight into the cosmic voids, vast, empty regions of space that contain very few galaxies or stars. These voids may seem like nothing, but they are an essential part of the universe's structure, and their study can tell us a great deal about the expansion of the universe and the way matter is distributed across vast distances. By observing the 21 centimeters signal from regions within and around these cosmic voids, we can learn more about their origins and how they fit into the broader cosmic puzzle. While the 21 cm hydrogen line is undoubtedly one of the most exciting tools we have for unlocking the mysteries of the early universe, we must also recognize that we are still in the early stages of using this data effectively. The technology required to detect and interpret the 21 cm signal is still being developed. Instruments like the Square Kilometre Array, SKA, which is set to become one of the largest radio telescopes in the world, will be key in collecting data from this elusive signal. However, even with such advanced technology, detecting the 21 cm hydrogen line is a monumental task, requiring incredible precision and careful data analysis. The signal is faint, and it is often drowned out by the noise of more powerful, nearby cosmic sources. This means that scientists must employ a range of techniques, from building massive networks of radio telescopes to developing sophisticated algorithms, in order to isolate and study the signal. There are also other challenges on the horizon. For example, the foreground noise that masks the 21 cm signal is a significant obstacle. This noise comes from a variety of sources, including the radiation emitted by our own galaxy, the Milky Way. Because the 21 cm hydrogen line is located in the same frequency range as many of these signals, isolating it from the noise is no easy feat. However, researchers are developing innovative techniques to filter out the noise, allowing the faint signal from the early universe to shine through. These techniques include using algorithms that can distinguish between different types of signals, as well as creating dedicated observatories specifically designed to study the 21 cm signal. As more advanced telescopes come online and we gather more data, the mysteries surrounding the 21 cm hydrogen line will continue to unfold. Every discovery brings us closer to understanding the birth of our universe and the forces that shaped it. The search for the 21 cm signal is a journey that could change the way we view the cosmos, providing us with the clearest picture yet of the early universe. The answers to some of our most profound questions about the cosmos are out there, waiting to be discovered. And as we peel back the layers of time, the 21 cm hydrogen line could be the key that unlocks the ultimate mysteries of the universe. As we continue to study the 21 cm hydrogen line, it's important to reflect on the immense implications it holds for our understanding of the universe. The ability to track the very evolution of matter from the dawn of the cosmos to its present state could completely reshape our models of cosmology. But the journey of uncovering these secrets is not just about collecting data. It's about interpreting that data and understanding what it tells us about the fundamental forces that govern everything in existence. One of the most profound revelations that the 21 cm hydrogen line could provide is insight into the large-scale structure of the universe. The distribution of galaxies, clusters, and voids in the universe is not random. It's the result of forces that have acted over billions of years, shaping the cosmic landscape. By detecting and analyzing the 21 cm signal from different regions of space, scientists can map out the distribution of hydrogen in the early universe and trace how it evolved into the complex structures we observe today. These maps would not just be static images. They would represent the evolution of the universe, showing how gravity, dark matter, and dark energy have influenced the distribution of matter. What's truly remarkable about the 21 cm hydrogen line is that it acts as a cosmic tracer that can reveal this structure with incredible detail. This hydrogen-based signal is not like visible light, which can be absorbed or scattered by intervening matter. The 21 cm signal travels freely through space, undisturbed by dust or other obstacles. This means that it can give us an untainted view of the universe's structure, even in the farthest reaches of space, and from a time long before galaxies as we know them had formed. It's almost like a snapshot of the universe's genetic blueprint, allowing us to see the raw materials that went into building the galaxies, stars, and cosmic structures that we observe today. As scientists analyze the 21 cm signal, they'll be looking for traces of cosmic fluctuations. These fluctuations are variations in the density of matter in the early universe that led to the formation of the first stars and galaxies. Studying how these fluctuations evolved over time can provide crucial insights into how the first structures formed and how the universe transitioned from a uniform soup of hydrogen and helium into the vibrant, heterogeneous cosmos we know today. These fluctuations are the fingerprints of the cosmic inflation that occurred just fractions of a second after the Big Bang. This period of rapid expansion, driven by the energy stored in quantum fields, set the stage for the universe's large-scale structure. The 21 centimeters hydrogen line can act as a time capsule, allowing us to peer back to this crucial phase of cosmic history and gain a deeper understanding of how it all began. The potential to unlock new knowledge about the dark ages of the universe is one of the most captivating aspects of the 21 centimeters hydrogen line. The Dark Ages refer to the period after the Big Bang and before the first stars, when the universe was devoid of visible light. During this time, the universe was filled with neutral hydrogen, which absorbed light and kept the cosmos shrouded in darkness. As we look back in time, using the 21 centimeter signal, we can explore the nature of this dark period in unprecedented detail. We could learn about the physical processes that governed the universe before the advent of stars, galaxies, and other luminous objects. Moreover, the 21 centimeters hydrogen line holds great promise for studying extragalactic space. Most of the studies of the early universe so far have relied on observations of distant galaxies or the cosmic microwave background, CMB, radiation. However, the CMB provides a snapshot of the universe's condition when it was just 380,000 years old, an early stage in the universe's evolution. By studying the 21 centimeters hydrogen line, however, we can directly trace the universe's state at a much later point, up to around 1 billion years after the Big Bang. This allows us to observe the universe at a key transitional moment, when galaxies were still forming and the universe was evolving from a hot, dense state into the cooler, more structured cosmos we observe today. The interactions between hydrogen and radiation are key to understanding the 21 centimeters hydrogen line. When ultraviolet radiation from the first stars and galaxies began to ionize the surrounding hydrogen gas, it changed the properties of the gas and left an imprint on the 21 centimeters signal. By studying this signal, we can probe the physical conditions of the early universe, including the temperature and density of hydrogen, the level of ionization, and the rate at which stars and galaxies were forming. This information will help scientists determine the timescale of reionization and reveal which sources were responsible for this process. One of the ongoing challenges of studying the 21 centimeters hydrogen line is the extremely faint nature of the signal. The signal we're detecting today has been traveling through the universe for billions of years, and as it moves through vast stretches of space, it gets weaker and weaker. Additionally, the cosmic expansion has stretched the signal to longer wavelengths, further diminishing its strength. To detect this elusive signal, scientists rely on highly sensitive instruments and innovative techniques. For instance, large arrays of radio telescopes, such as the Low Frequency Array, LOFAR, and the Square Kilometer Array, SKA, are being built to collect the faint signals from across the sky and piece them together. But it's not just about having the most powerful telescopes. It's also about improving our data analysis methods to filter out unwanted noise and extract meaningful information from the signal. One of the primary hurdles in interpreting the 21 centimeter signal is the interference from foreground emissions. These emissions come from a variety of sources, including our own galaxy, the Milky Way, as well as the solar system, and even Earth-based radio signals. These foreground signals are much stronger than the faint 21 centimeter signal and can easily drown it out. To isolate the 21 centimeter signal, scientists employ sophisticated techniques like foreground subtraction and statistical methods to remove unwanted noise and reveal the true signal. In many ways, studying the 21 centimeters hydrogen line is like trying to hear a whisper in a noisy room. The better the tools and techniques we develop, the more clearly we'll be able to hear that whisper and understand the messages it's trying to convey. Even with these challenges, the potential for breakthroughs in our understanding of the universe remains immense. As our telescopes become more advanced, and as we develop better methods for analyzing the 21 centimeters signal, we'll be able to answer some of the most profound questions about the universe's origins. How did the first stars and galaxies form? What were the conditions of the universe just after the Big Bang? How did cosmic structures like galaxies and clusters of galaxies emerge from the primordial hydrogen fog? These are the questions that the 21 cm hydrogen line may help us answer, and in doing so, it could unlock the deepest mysteries of the universe. The 21 cm signal is also a powerful tool for understanding the nature of dark matter. While we cannot directly observe dark matter, we know that it exerts a gravitational influence on the visible matter in the universe. Dark matter's effects can be seen in the way galaxies rotate, the formation of large-scale cosmic structures, and the gravitational lensing of distant objects. The 21 cm signal could offer a new way to study dark matter, as it may interact with hydrogen in ways that could reveal its properties. While dark matter is notoriously difficult to detect, the 21 cm signal could provide an indirect yet valuable way to study it, shedding light on one of the most elusive and mysterious components of the cosmos. As we continue to push the boundaries of what we know about the universe, the 21 cm hydrogen line will undoubtedly play a central role. From unveiling the secrets of the early universe to helping us understand the cosmic structure and even offering new insights into dark matter, this mysterious radio signal holds the potential to answer questions that have been lingering for centuries. The next few decades will be a thrilling time for cosmology, as new discoveries unfold, and we begin to piece together the cosmic puzzle in unprecedented detail. As we look to the future, the study of the 21 cm hydrogen line is poised to dramatically change how we think about the cosmos. The information we gain from this line is essential not only for understanding the formation of galaxies but also for providing deeper insights into the evolution of cosmic phenomena that we have yet to fully comprehend. One exciting possibility that scientists are working to investigate is the ability to use the 21 cm signal to probe regions of space that are extremely distant from us, enabling us to study the most ancient parts of the universe in ways that were previously thought impossible. A key to unlocking these insights lies in the way we combine different methods of observation. Traditional methods, such as studying the cosmic microwave background (CMB), provide an excellent snapshot of the universe when it was only about 380,000 years old. However, the 21 cm hydrogen line lets us reach even further back, tracking the universe's growth before stars even lit up the sky. This gives us a unique opportunity to study the epoch of reionization, a period between 100 million and 1 billion years after the Big Bang when the first stars began to form, emitting ultraviolet light that reionized the surrounding hydrogen gas. The detailed mapping of this era will not only help us understand when the first light emerged in the universe but also how the very building blocks of our universe evolved during this crucial time. One of the key aspects of the 21 cm hydrogen line is that it provides a window into cosmic history that no other current observational technique can. The 21 cm signal is a remnant of the universe's infancy, carrying with it information that has been preserved for billions of years. As we improve our technology to detect this faint signal and reduce interference from cosmic background noise, we'll gain access to unprecedented data about the early universe, including the rates at which stars and galaxies were born and how they interacted with one another. This opens up new questions and lines of inquiry, such as, did galaxies form in isolation, or did they cluster together in more complex ways than we currently understand? The 21 cm hydrogen line also holds the potential to enhance our understanding of cosmic inflation, the theory that proposes the universe underwent a rapid and exponential expansion in the moments following the Big Bang. While the theory has already been supported by indirect evidence, such as the uniformity of the CMB, the 21 cm line can help confirm some of the details of this period. By studying how the hydrogen gas interacted with the radiation from the early universe, we can gain direct insight into the inflationary process and potentially uncover new details about the physics that drove the rapid expansion. One area of study that could greatly benefit from the 21 cm hydrogen line is the investigation of cosmic voids, vast regions of space that contain little or no matter. These voids are the largest known structures in the universe, and they are still somewhat poorly understood. By tracing the distribution of hydrogen in these voids, we can learn more about their formation and growth, as well as their role in shaping the overall structure of the universe. The data collected from the 21 centimeter signal will allow us to study these voids in greater detail than ever before, offering a deeper understanding of how they evolve and how they influence the surrounding galaxies and structures. The question of whether we are truly alone in the universe is one that has fascinated humanity for centuries. The 21 centimeters hydrogen line might even help us in the search for extraterrestrial life. By studying the distribution of hydrogen and other elements in distant galaxies, we can begin to investigate whether the conditions for life as we know it exist elsewhere in the cosmos. Hydrogen is the most abundant element in the universe, and understanding how it behaves and interacts with radiation in different environments will give us key insights into whether planets capable of supporting life could exist in other parts of the galaxy. Furthermore, any anomalies or deviations in the 21 centimeter signal that deviate from our expectations could indicate the presence of alien civilizations or technological signatures. In addition to these incredible possibilities, the study of the 21 centimeters hydrogen line offers important applications in other areas of physics. For instance, the 21 centimeter signal could provide clues about the properties of dark energy, the mysterious force believed to be driving the accelerated expansion of the universe. Although the exact nature of dark energy remains unknown, it is thought to make up about 68% of the total energy content of the universe. By carefully studying how the hydrogen gas interacts with dark energy across time, scientists may gain new insights into this elusive force and its role in shaping the fate of the universe. The study of the 21 centimeter signal is not just a purely academic pursuit, it also presents exciting technological challenges and innovations. As researchers continue to build more advanced radio telescopes, such as the Square Kilometer Array, SKA, and Low Frequency Array, LOFAR, new technologies are being developed to improve the sensitivity and precision of these instruments. The ability to detect and interpret the 21 centimeter signal requires cutting-edge technology and techniques, such as ultra-sensitive receivers, advanced algorithms for signal processing, and precision calibration methods. These innovations will have far-reaching effects, potentially benefiting other areas of science and engineering, from communication technologies to materials science. One area where we might see the most immediate applications is in space exploration. If the 21 centimeter signal can be successfully detected in regions of space far beyond our current reach, it could enable us to map the entire observable universe in unprecedented detail. This could not only help us understand the origins and evolution of galaxies, but also give us a clearer picture of what lies beyond our own galaxy. Mapping the distribution of hydrogen across vast cosmic distances could even provide new insights into the nature of the universe's expansion and the overall structure of the cosmos. Yet, as promising as this line of research is, we must remember that there is still much we don't know. While the 21 centimeters hydrogen line is a tool that holds immense potential, its study also faces significant challenges. The signal itself is incredibly faint, and the vast distances it travels through space mean that it is subject to interference and distortion. Even with the most powerful telescopes at our disposal, isolating the 21 centimeter signal from other sources of radio noise is no easy task. Researchers are constantly refining their techniques to make the most of the data they collect, developing new algorithms and methods to filter out unwanted noise and focus on the faintest signals. These challenges require both creative problem-solving and collaboration between scientists, engineers, and technologists from around the world. Despite these difficulties, the future of the 21 centimeters hydrogen line research looks incredibly promising. With advancements in observational techniques and an ever-growing understanding of the universe's fundamental processes, we are poised to make exciting discoveries in the coming years. By continuing to study the 21 centimeters hydrogen line, we may unlock secrets about the very origins of the universe, the formation of galaxies, and the forces that shape the cosmos. The potential for new insights and discoveries is vast, and with each breakthrough, we get one step closer to understanding the grand tapestry of space and time. As this field of research evolves, we can only imagine how our understanding of the universe will deepen. The 21 centimeters hydrogen line is a key that opens the door to an entirely new chapter in cosmology. It may be a signal that is only now starting to be understood, but it holds the promise of revealing far more than we can even begin to comprehend. As we continue to investigate this fascinating aspect of space, we may find that the universe's deepest mysteries are not as distant or as unknowable as they once seemed. As we move forward with our understanding of the universe, the 21 centimeters hydrogen line will undoubtedly play a pivotal role in answering some of the most profound questions in cosmology. The mysteries it holds about the early universe, the formation of galaxies, the epoch of reionization, and potentially even the nature of dark energy are just the beginning. As scientists continue to refine their techniques for detecting this faint signal and analyze the data, we are sure to witness a revolution in our understanding of space. One of the most exciting aspects of the 21 centimeters hydrogen line is its potential to provide insights into cosmic expansion. By studying the properties of the hydrogen gas over large cosmic scales, we may be able to better understand the rate at which the universe is expanding. This has implications for fundamental physics, as the rate of expansion is tied to critical aspects of the universe's structure and evolution. Currently, there are discrepancies in the measurements of the expansion rate, known as the Hubble constant, when calculated using different methods. The 21 centimeter signal might offer a new, independent way to measure this constant and resolve these conflicts, providing one of the most important pieces of the puzzle in modern cosmology. At the core of these advancements in cosmology is the technology that makes them possible. The detection of the 21 centimeters hydrogen line relies on sophisticated equipment capable of observing radio waves that have traveled billions of light-years through space. This means that researchers must rely on highly sensitive radio telescopes capable of detecting extremely faint signals in the presence of various sources of cosmic and terrestrial noise. One of the most prominent efforts in this field is the construction of the Square Kilometre Array, SKA, a project that aims to create the world's largest radio telescope, with over 1 million square meters of collecting area. With its advanced technology, the SKA promises to make unprecedented observations of the 21 centimeter signal, allowing us to map the universe with incredible resolution and precision. The importance of the SKA extends beyond just the 21 centimeters hydrogen line. Its cutting-edge technology will be instrumental in answering a wide range of questions about the cosmos, from the formation of galaxies to the properties of dark matter. But when it comes to the 21 centimeter signal, the SKA's ability to detect faint radio waves and observe distant parts of the universe will be a game-changer. This massive telescope, in conjunction with other observational tools, will allow us to probe parts of the universe that were previously beyond reach. Another aspect of the 21 centimeters hydrogen line's potential lies in its ability to enhance our understanding of the cosmic web. The cosmic web is the large-scale structure of the universe, consisting of vast filaments of galaxies and gas that form a network stretching across the cosmos. These filaments are thought to have formed in the early universe, and studying them can help us understand how matter has been distributed across space over billions of years. By using the 21 centimeter signal to map out these structures, scientists can gain a deeper understanding of how galaxies and other cosmic features evolved over time. This could provide clues about the role of dark matter in shaping the universe's structure and help us understand the forces that govern its growth. At a more fundamental level, the study of the 21 centimeters hydrogen line is helping us to refine our understanding of atomic physics. The 21 centimeters transition itself is a result of the quantum mechanical interaction between the hydrogen atom's electron and proton. By studying this transition in detail, scientists can gain insights into the properties of hydrogen and how it behaves in different cosmic environments. These insights could have applications beyond cosmology, potentially benefiting fields such as material science and nuclear physics. The 21 centimeters signal also offers an opportunity to probe the intergalactic medium, the sparse hydrogen gas that fills the vast spaces between galaxies. The properties of the intergalactic medium are still not fully understood, and the 21 centimeters signal provides a unique way to study it. By observing how the signal is affected as it travels through this medium, researchers can learn about the temperature, density, and composition of the gas, which will deepen our understanding of how the universe's matter is distributed. As promising as all these prospects are, it is important to acknowledge the challenges that still lie ahead. One of the biggest obstacles in the study of the 21 cm hydrogen line is the interference from foreground signals, that is, radio waves generated by objects within our own galaxy. The Milky Way, for instance, emits a large amount of radio radiation that can easily drown out the faint 21 cm signal from distant galaxies. To overcome this, scientists must develop highly advanced signal processing techniques to isolate the 21 cm signal from the background noise. This is a task that requires not only powerful telescopes but also innovative algorithms capable of distinguishing the desired signal from the noise. Moreover, because the 21 cm signal is so faint and travels across vast distances, it can become distorted by the cosmic environment through which it passes. The gas and dust that exist in between galaxies can scatter or absorb the radio waves, changing the characteristics of the signal. This means that in order to extract accurate information, astronomers must develop methods to correct for these distortions. This challenge is compounded by the fact that the signal is not uniform. It can vary depending on the density and temperature of the hydrogen gas it interacts with. Understanding these variations requires a deep knowledge of both the physical processes that affect the signal and the observational techniques needed to account for them. In the near future, the advancements in radio astronomy and computational methods are expected to help overcome many of these hurdles. By combining efforts from various research teams and leveraging the power of international collaborations, we will be able to tackle the challenges posed by the 21 cm hydrogen line and make strides in our understanding of the universe's most profound mysteries. The potential rewards are great, and the breakthroughs that lie ahead will undoubtedly reshape our view of the cosmos. The discovery and study of the 21 cm hydrogen line represent more than just a technological triumph. It's a window into the very fabric of the universe. It is a tool that allows us to peer into the distant past, to trace the steps of the universe's evolution, and to investigate some of the most fundamental aspects of physics. It offers a glimpse of what is possible when science, technology, and curiosity come together to answer the biggest questions humanity has ever asked. We are standing on the cusp of a new era in space exploration. The 21 cm hydrogen line has the potential to reveal the cosmos as we have never seen it before, and the discoveries that await us are sure to be groundbreaking. As we continue to refine our tools and expand our understanding, we are on the brink of unlocking the secrets of the universe, one faint radio wave at a time. The journey ahead is long, but with each step forward, we will continue to unveil the mysteries that have eluded us for centuries. The future of the 21 cm hydrogen line research is exciting, not only because of its potential to provide unprecedented views into the early universe but also due to the new questions it may raise. With the data gathered through the study of this elusive signal, we may find ourselves uncovering new phenomena, some of which could reshape our understanding of astrophysics entirely. We are at the precipice of discovering phenomena that could extend far beyond the scope of current theoretical models. One particularly thrilling aspect of the ongoing research on the 21 cm hydrogen line is its capacity to provide insights into the epoch of reionization. This epoch, which occurred around 13 billion years ago, marks the transition from an opaque universe to a transparent one. The early universe, immediately after the Big Bang, was a hot, dense fog of hydrogen and helium ions. As the universe cooled, hydrogen atoms were able to form, but this gas was still too warm to allow light to travel freely, leaving the universe in a state of opacity. However, over time, as the first stars began to form, their radiation was intense enough to ionize the surrounding hydrogen gas. This process, called reionization, gradually made the universe more transparent. The 21 cm hydrogen line is crucial for studying this period because it allows us to observe the state of the hydrogen gas before and after reionization, providing clues about how and when this monumental phase occurred. The detection of the 21 cm signal from distant galaxies and regions far beyond our local universe has the potential to reveal the full timeline of reionization. This would allow scientists to pinpoint exactly when the first stars and galaxies formed, shedding light on one of the universe's most important transitions. By analyzing the 21 cm signal, we could even uncover details about the first light emitted by stars and galaxies, offering a deeper understanding of the processes that led to the formation of the cosmic structures we see today. Beyond the epoch of reionization, the 21 cm signal holds the promise of unlocking even more mysteries about the nature of dark matter. Dark matter remains one of the greatest enigmas of modern physics. It doesn't emit, absorb, or reflect light, making it invisible to conventional detection methods. Yet, we know that dark matter exists because of its gravitational influence on galaxies and galaxy clusters. Despite its gravitational effects being well documented, its true nature remains unknown. Could the 21 cm signal provide a clue about dark matter? It's possible. Some theoretical models suggest that interactions between dark matter and normal matter could influence the 21 cm signal. For example, dark matter could affect the temperature of the hydrogen gas or alter how it interacts with radiation. If these effects can be detected through the 21 cm hydrogen line, they could help scientists gain critical insights into the nature of dark matter and its role in the formation of the universe's structures. While current research has primarily focused on the 21 cm signal's implications for understanding the early universe, as more data is gathered, new avenues for exploration will undoubtedly emerge. We might discover unexpected connections between the signal and other cosmic phenomena, such as the nature of cosmic inflation, or even the possible existence of exotic forms of matter and energy. The more we look into the universe's distant past, the more mysteries we uncover, and the more our understanding of physics and cosmology is deepened. For now, much of the study of the 21 cm hydrogen line remains in its early stages. The technology to detect this faint signal with the required precision is still developing, and many observational challenges remain. Yet, with advances in radio telescopes and data processing algorithms, we are steadily improving our ability to extract meaningful information from the 21 cm signal. As our technological capabilities evolve, we may begin to see clearer images of the cosmic dawn, the period when the first stars and galaxies illuminated the universe. The 21 cm hydrogen line is like a cosmic fingerprint that holds the key to tracing the origins of everything we know. It's an incredibly valuable tool, one that has the potential to reveal not just the history of galaxies, but also the fundamental processes that govern the cosmos. In the coming decades, with the continued advancement of radio astronomy, we are poised to unveil the most detailed and comprehensive views of the universe's infancy. Every breakthrough will be an opportunity to step deeper into the fabric of the cosmos, peeling back layers of cosmic history that were once hidden in darkness. As we learn to listen more carefully to the faint whispers of the universe encoded in the 21 cm hydrogen line, we will continue to expand our understanding of the vast, interconnected system in which we live. The 21 cm hydrogen line represents a bridge to the distant past, a way to glimpse the universe's earliest moments. It is a reminder that even in the void of space, there is an incredible wealth of information waiting to be discovered. By studying the universe's faintest signals, we unlock secrets that can help us understand not just the cosmos but the fundamental nature of existence itself. The mysteries of the 21 cm hydrogen line are just beginning to unfold, and as we continue to probe the cosmos with ever greater precision, the answers will begin to emerge. As we look forward to the discoveries of the next decades, we are reminded of the vastness of the cosmos, the complexity of the universe, and the boundless potential of human curiosity. The study of the 21 cm hydrogen line is just one piece of this grand puzzle, but it is a key piece. A piece that promises to lead us to greater understanding and new frontiers in cosmology, astrophysics, and beyond. The future of space exploration lies in the faint signals of the past, and the 21 cm hydrogen line may be one of the most important clues yet. With continued technological advancements and deeper exploration, we may one day fully unlock the secrets of the universe, one radio wave at a time. The potential of the 21 cm hydrogen line to reshape our understanding of the universe cannot be overstated. As we dive deeper into the study of this signal, we are not only uncovering the events that shape the cosmos but also probing the very fabric of reality itself. While scientists have made incredible strides in developing the tools necessary to capture the faint whispers of the 21 cm line, much work still lies ahead. The mysteries it holds are tantalizing, and with each passing discovery, the world of astrophysics grows even more exciting. One of the most intriguing possibilities lies in the future of 21 centimeters tomography, which could provide us with three-dimensional maps of the early universe. Just as traditional tomography allows doctors to see the internal structure of the human body through X-rays, 21 centimeters tomography could provide a detailed view of how matter and light interacted in the young universe. By capturing and analyzing the 21 centimeters hydrogen signal across different regions of space, we could create an intricate map of the universe's earliest structures, tracing the formation of galaxies, star clusters, and other cosmic objects. This new form of mapping could help us answer some of the most profound questions in modern science. How did the first galaxies form and evolve? What role did the first stars play in shaping the universe? What caused the great cosmic transformation from a hot, dense fog to the vast, starry universe we see today? The 21 centimeters hydrogen line is a crucial piece of this puzzle, offering a window into a time when the universe was very different from what we observe today. The quest for understanding the epoch of reionization also hinges on the ability to decipher the 21 centimeters signal. As previously mentioned, the period of reionization marks the transition from a universe filled with neutral hydrogen to one dominated by ionized gas. This shift is pivotal for understanding the formation of cosmic structures and the role of radiation feedback in this process. While much is known about the effects of the first stars and galaxies on their surrounding environments, the precise mechanics of reionization remain elusive. Researchers are eager to measure the signal from the 21 centimeters line across vast regions of space to help pinpoint exactly when reionization began and ended. This will provide an unprecedented view into the timeline of cosmic evolution. By observing the variations in the 21 centimeters signal, scientists can study the growth of cosmic structures and the complex interactions between matter and radiation, unveiling new details about the environment that gave rise to the first galaxies and stars. Another exciting aspect of the 21 centimeters signal study is its potential to challenge our current understanding of cosmological models. As we continue to uncover new data and refine our techniques for observing the faint 21 centimeters signal, scientists are bound to encounter surprises that force us to reconsider long-held assumptions about the universe. For example, some models of the early universe predict that the 21 centimeters signal would be smoother and more uniform than what has been observed in some data sets, leading to speculation that there may be unknown factors at play. Could these anomalies suggest that we are missing a key component of the universe's formation? These irregularities might point to new types of cosmic phenomena, such as previously unknown forms of dark matter or new forces of nature that influenced the early universe. In this sense, the study of the 21 centimeters hydrogen line could serve as a sort of cosmic experiment, pushing the boundaries of our understanding and prompting us to explore new theories and hypotheses about the workings of the cosmos. While much of the research surrounding the 21 centimeters signal is still in its early stages, the discoveries made thus far have already revolutionized the way we think about the early universe. The ongoing efforts to refine our detection methods and analyze the data are laying the foundation for a new era in cosmology, where we will be able to answer questions that have puzzled humanity for centuries. It's a reminder that even in the vast emptiness of space, there is a wealth of knowledge waiting to be uncovered. At the same time, as we push the boundaries of scientific knowledge, we must remember that the study of the 21 centimeters hydrogen line represents only one facet of a much larger cosmic exploration. As we continue to develop new telescopes and technologies capable of observing distant parts of the universe, we will be able to piece together a more complete picture of the cosmos. With each discovery, we move closer to understanding the true nature of the universe, its origins, and its eventual fate. The quest to understand the 21 centimeters hydrogen line also represents a broader effort to understand the origins of life and the possibility of life elsewhere in the universe. As we explore the early universe, we are learning not only about the physical processes that gave rise to galaxies and stars but also about the conditions that might support the development of life. The chemical ingredients for life as we know it, such as carbon, oxygen, and nitrogen, are thought to have been created in the hearts of stars and spread throughout the universe through processes like supernovae. By studying the 21 centimeter signal, we could uncover more details about the conditions in the early universe that led to the formation of elements crucial for life. If the 21 centimeters hydrogen line can provide us with a clearer understanding of how galaxies and stars formed, it may also offer insights into how the building blocks of life emerged and how life could potentially arise elsewhere in the cosmos. In this way, the 21 centimeters signal is not just a tool for studying the past, but also a means of understanding the broader cosmic context in which life might exist. The study of the 21 centimeters hydrogen line is also a reminder of the incredible technological advancements that are necessary for exploring the universe. Detecting such a faint signal requires state-of-the-art radio telescopes and advanced data processing techniques. As astronomers and physicists continue to improve these technologies, they will not only unlock the secrets of the 21 centimeters signal but also enhance our ability to explore the entire electromagnetic spectrum, from the visible light we can see to the high-energy gamma rays that reveal the most extreme phenomena in the universe. As we progress further into the 21st century, the search for the 21 centimeter signal will undoubtedly lead to groundbreaking discoveries that push the limits of human knowledge. It is an exciting time for space research, as the mysteries of the universe, both near and far, are slowly being revealed. Through continued collaboration, innovation, and determination, we will gain new insights into the origins and evolution of the cosmos, helping us answer some of the biggest questions that humanity has ever asked. As the study of the 21 centimeters hydrogen line continues to unfold, it's important to recognize the broader implications of these discoveries, not just in the field of astrophysics, but across the entire scientific community. This research is deeply connected to our pursuit of fundamental physics and our understanding of the laws that govern the universe. The 21 centimeter signal, being such a sensitive probe of the early universe, provides an invaluable opportunity to test and refine models of cosmology, dark matter, and even the fundamental forces of nature. One of the most intriguing possibilities in this area is the role that dark matter might play in shaping the early universe. While dark matter has been observed through its gravitational effects on galaxies and galaxy clusters, it has never been directly detected. The 21 centimeter signal might hold the key to uncovering new clues about this mysterious substance. Some theorists suggest that dark matter could interact with neutral hydrogen in a way that leaves an imprint on the 21 centimeters line, altering its characteristics. If this interaction were detectable, it could offer the first direct evidence of dark matter's influence on the formation of cosmic structures. Additionally, the study of the 21 centimeters hydrogen line could provide us with insight into the behavior of inflation, the rapid expansion of the universe that occurred just fractions of a second after the Big Bang. Inflationary theory, which explains how the universe expanded faster than the speed of light in its earliest moments, is one of the cornerstones of modern cosmology. However, certain aspects of inflation remain speculative, and the 21 centimeters signal may hold the potential to test some of these ideas. The temperature fluctuations in the cosmic microwave background (CMB) have already provided clues about inflation, but the 21 centimeters signal could give us even more direct information about the density fluctuations in the early universe that helped drive the formation of galaxies and other large-scale structures. The next major step in the study of the 21 centimeters signal involves the development of next-generation radio telescopes, which are designed specifically to observe this faint signal from deep space. Among the most promising projects are the Square Kilometer Array, SK, and the Low Frequency Array, LOFAR, both of which are being constructed with the goal of detecting the 21 centimeters hydrogen line across vast regions of the sky. The SK, which is currently under construction in South Africa and Australia, will be one of the largest radio telescope arrays in the world, with an effective collecting area of over 1 square kilometer. This massive array will have the sensitivity and resolution needed to detect the subtle variations in the 21 centimeter signal that will help us map the early universe in unprecedented detail. LOFAR, another cutting-edge radio telescope, is already operational and has made significant contributions to the study of the 21 centimeters line. This array is designed to detect low-frequency radio waves and has already provided valuable data that supports the theory of reionization. By analyzing the 21 centimeter signal, LOFR and similar telescopes will allow scientists to detect subtle features in the signal that could reveal new information about the first stars, galaxies, and the processes that shape the universe's evolution. With the data these telescopes provide, researchers are hopeful that they will be able to create more accurate models of cosmic history. The potential of these future instruments is immense. However, it's important to remember that the detection of the 21 centimeter signal from the early universe presents significant technical challenges. The signal is incredibly faint, and its detection requires a level of precision that is beyond the capabilities of current technology. Furthermore, the signal is easily masked by noise from other sources, such as galactic and extragalactic radio emissions. To overcome these challenges, astronomers are developing increasingly sophisticated techniques for signal processing and data analysis. Advanced algorithms and machine learning methods are being used to isolate the 21 centimeter signal from the noise and to correct for any distortions caused by the Earth's atmosphere or the telescopes themselves. As we continue to improve our observational tools, the study of the 21 centimeters hydrogen line will undoubtedly lead to a wealth of new insights. Some of the most exciting prospects include the potential discovery of cosmic anomalies or previously unknown phenomena. For example, researchers have speculated that the 21 centimeter signal might reveal the existence of new types of astrophysical objects, such as primordial black holes, that could have formed in the early universe. These objects, if they exist, could help us answer questions about the origins of black holes and the processes that govern their growth in the early stages of cosmic evolution. Furthermore, as we improve our ability to measure the 21 centimeters line with greater precision, we may also be able to probe the influence of exotic physics on the formation of the universe. For instance, the study of the 21 centimeter signal could reveal subtle signatures of phenomena such as cosmic strings, hypothetical one-dimensional defects in spacetime that might have formed during the early universe. These structures, if they exist, could have profound implications for our understanding of the fundamental nature of space and time. While the detection of cosmic strings is still speculative, the 21 centimeters line might provide a way to test their existence by observing how they would affect the formation of the universe's earliest structures. The implications of these discoveries extend far beyond just astrophysics. The insights gleaned from the study of the 21 centimeters hydrogen line could also have profound effects on our understanding of philosophical questions related to the nature of existence, time, and the universe itself. How did the universe emerge from an incomprehensible singularity into the vast, complex cosmos we see today? What role does our understanding of the early universe play in our perception of time, space, and the very nature of reality? These questions may seem abstract, but they are deeply connected to the exploration of the cosmos and the pursuit of knowledge. As we push the boundaries of human understanding, we are not only uncovering the mysteries of the universe but also engaging in a search for meaning and connection in a vast and seemingly infinite cosmos. The study of the 21 centimeters hydrogen line offers an exciting glimpse into the future of cosmology and astrophysics. The discoveries that will arise from this field of research are bound to reshape our understanding of the universe's origins, its evolution, and the forces that have shaped it. From revealing the formation of galaxies and stars to providing insights into the nature of dark matter and inflation, the 21 centimeters signal promises to be one of the most important tools in modern science. As we continue to develop the technology and techniques needed to detect and analyze the faint 21 centimeters signal, the mysteries of the early universe will slowly come into focus. It's an exciting time to be involved in this area of research, and the potential for new discoveries is limitless. With each breakthrough, we are one step closer to unlocking the secrets of the cosmos, discovering the forces that shaped our universe, and understanding our place within it. The future of 21 centimeters hydrogen line research is only just beginning, and as we venture deeper into the universe's history, we are not only looking back in time but also opening the door to entirely new realms of scientific discovery. The more we understand the nature of the universe's formation and evolution, the more we unlock answers to fundamental questions that have been at the heart of humanity's quest for knowledge for centuries. One of the most exciting developments in the field of cosmology is the potential for cosmic tomography. This method, which involves using the 21 cm hydrogen line to create detailed three-dimensional maps of the universe, could revolutionize our understanding of cosmic structures. Just like an MRI scan provides detailed images of the human body, cosmic tomography offers the potential to visualize the universe in a way we've never done before. By mapping the distribution of neutral hydrogen in the early universe, we could create detailed portraits of the first galaxies, stars, and even the first black holes. These maps could reveal how these objects formed and how they influenced the subsequent evolution of the universe. The creation of these cosmic maps will depend heavily on the precision of the 21 cm signal measurements. Researchers are already developing techniques to combine data from different sources, including existing radio telescopes and upcoming observatories like the James Webb Space Telescope, JWST, which will provide complementary infrared data. The combination of different wavelengths of light and radio frequencies will allow scientists to build a much clearer and more complete picture of the early universe, combining observations of both gas clouds and stars. The goal is to eventually create a detailed 3D structure of the universe's evolution from the time before stars formed to the present day. In parallel with these advances, astronomers are investigating the potential of the 21 cm hydrogen line to reveal new phenomena within the intergalactic medium, IGM, the vast regions of space between galaxies. This IGM is not empty but filled with gas, much of it hydrogen. Understanding the properties of this gas is crucial because it helps determine how galaxies form, how they evolve, and how they are influenced by external forces. The 21 cm signal could provide us with unprecedented details about this otherwise invisible matter, offering insights into the conditions that led to the formation of the first stars and galaxies. An intriguing aspect of the 21 cm signal is how it may shed light on the nature of space itself. The fact that this signal is so faint and difficult to detect raises the question, how does the universe evolve to the point where these distant, barely perceptible signals can be studied in such detail? This involves considering the underlying fabric of spacetime and how the large-scale structure of the universe, such as the expansion and gravitational effects, influence the propagation of light and radio waves. As we develop our understanding of these effects, we might gain insights into quantum gravity, the elusive theory that seeks to explain how gravity interacts with quantum mechanics. Understanding how the 21 cm signal behaves on cosmological scales could provide indirect evidence of quantum effects that we have yet to observe directly. The potential for discovering new physics is also a driving force behind the exploration of the 21 cm signal. As we continue to study this faint and distant signal, we are beginning to probe not only the universe's past but also the possibility that unknown forces or particles could have existed in the early universe. For example, there are theories that suggest the existence of dark radiation, a form of energy or particles that could have interacted with the hydrogen gas in the early universe, affecting the 21 cm signal in subtle ways. If dark radiation exists, its interaction with the 21 cm line could be detectable, offering us an entirely new way to study the properties of the universe's earliest moments. Moreover, understanding the 21 cm hydrogen line could offer us insights into the geometry of the universe. The distribution of neutral hydrogen in the early universe is influenced by the way space itself is structured. The geometry of the universe, whether it is flat, open, or closed, affects how light and radiation propagate through it. By mapping the 21 cm signal, we can better understand the overall shape of the universe and how it has evolved over time. The detection of any distortions or variations in the signal could provide clues about the expansion history of the universe and whether there are regions where the fabric of spacetime is behaving differently than we expect. In addition to answering questions about the early universe, the 21 cm hydrogen line holds promise for answering some of the biggest mysteries of the present day. One of the most pressing of these questions is the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy has been observed through its effect on the cosmos, its true nature remains one of the greatest unsolved puzzles in modern science. The study of the 21 cm line could provide critical data that helps us understand whether dark energy has been present since the universe's earliest moments, and how it has evolved over time. Equally important is the potential for the 21 cm signal to help scientists study the reionization era, the period in the universe's history when the first stars and galaxies formed and ionized the surrounding hydrogen gas. This process, known as cosmic reionization, is a critical moment in the history of the universe. Understanding the details of this phase will help us grasp how galaxies evolved and how the conditions necessary for life, as we know it, came into being. The 21 cm line is one of the most promising tools to probe this era, allowing us to directly observe the ionization process and its impact on the surrounding gas. As we develop our ability to detect and interpret the 21 cm signal, we can expect to see more and more groundbreaking discoveries that reshape our understanding of the cosmos. The deeper we look into the universe's history, the more we will learn not only about the universe itself but also about the laws of physics and the fundamental nature of reality. This is a process that will continue to challenge our imaginations, push the boundaries of technology, and inspire future generations of scientists to reach for new heights in their quest for knowledge. With the advancements in observational techniques, computational methods, and international collaboration, the study of the 21 cm hydrogen line is poised to revolutionize our understanding of the universe's birth, its ongoing evolution, and its ultimate fate. In the coming decades, as we develop the next generation of radio telescopes and analyze the vast amounts of data they produce, the mysteries of the early universe will become clearer, revealing a more complete picture of the cosmos than we ever thought possible. As this field of research continues to grow and evolve, one thing is certain: the 21 cm hydrogen line holds the key to some of the most profound and exciting discoveries in modern science. From unraveling the mysteries of the universe's earliest moments to testing the boundaries of physics itself, the 21 cm signal will undoubtedly be one of the most important scientific achievements of the 21st century. As we continue to develop and refine our understanding of the 21 cm hydrogen line, we must acknowledge the limitations and challenges we still face. The detection of such faint signals requires an unprecedented level of sensitivity and precision, and as we push the boundaries of technology, even the smallest sources of interference can hinder our progress. Radio telescopes, for instance, must be designed to filter out man-made noise, like signals from cell towers, satellites, and even spacecraft, while still picking up the incredibly weak signals from the distant cosmos. This is no easy feat, and it requires not only state-of-the-art hardware but also innovative software capable of processing the vast amounts of data generated by these instruments. The next-generation radio telescopes being developed to study the 21 cm hydrogen line are incredibly sophisticated. For example, the Square Kilometre Array, SKA, an international radio telescope project under construction in Australia and South Africa, promises to be the most powerful radio telescope ever built. It will be able to map the universe at unprecedented resolution and sensitivity, allowing scientists to study the 21 cm line in more detail than ever before. This project, set to begin its first phase of operations in the 2020s, will likely be the game-changer in understanding the 21 cm signal's potential. By integrating thousands of radio antennas across vast distances, the SKA will offer both exceptional sensitivity and angular resolution, allowing us to trace the history of hydrogen in the universe in ways that were previously unimaginable. Another exciting project is the HERA, Hydrogen Epoch of Reionization Array, in South Africa, which is dedicated to studying the 21 cm signal during the reionization epoch. This experiment focuses specifically on detecting the subtle variations in the 21 cm signal that could reveal the first galaxies and the processes that reionize the universe. HERA, while smaller in scale than the SKA, is designed with a unique set of antennas that aim to maximize sensitivity to the faint hydrogen signal from the distant universe. The data gathered by HERA could provide crucial insights into one of the most enigmatic phases of cosmic evolution, the epoch of reionization. The success of these projects will rely heavily on collaboration between astronomers, physicists, and engineers from all around the world. International cooperation has been a cornerstone of many of the largest and most ambitious scientific endeavors in history, and the study of the 21 centimeters hydrogen line is no exception. By pooling resources, knowledge, and technology from different countries and institutions, scientists can overcome the limitations of any single project and move closer to answering the fundamental questions that have driven our curiosity about the cosmos. Despite the incredible promise of these telescopes and their future contributions, one of the greatest hurdles scientists face is interpreting the data they collect. While we are now capable of detecting the 21 centimeters hydrogen line, its interpretation is a complex challenge. The signal is influenced by many factors, including the density of hydrogen, the temperature of the surrounding gas, and even the underlying geometry of space itself. These factors are not straightforward to model, and small errors in our understanding of these variables can lead to vastly different interpretations of the data. To solve this, scientists must develop more accurate computational models, which will require enormous computational power to simulate the vast scales involved. This brings us to the importance of computational astrophysics, the intersection of astronomy and advanced computing. The data from radio telescopes like the SKA and Hera must be processed, analyzed, and modeled in a way that accounts for the many variables at play. Complex simulations are needed to reconstruct the conditions of the early universe, and these simulations rely on supercomputers capable of processing billions of data points. As our computational capabilities improve, so too will our ability to interpret the 21 centimeters signal, ultimately leading to more precise and accurate models of cosmic evolution. Furthermore, the role of machine learning in processing 21 centimeters data cannot be overstated. With vast amounts of data coming in from multiple telescopes, traditional methods of data analysis are becoming increasingly inadequate. Machine learning algorithms, which can learn patterns in data and make predictions based on previous observations, offer a powerful tool for identifying subtle features in the 21 centimeters signal that might otherwise go unnoticed. By training algorithms on large datasets, astronomers can refine their models, helping to distinguish between various cosmic phenomena and accurately pinpoint the origin of the signals they detect. The collaboration between radio astronomy and cosmology will also play a crucial role in advancing our understanding of the 21 centimeters hydrogen line. While radio telescopes provide the tools to detect and study the faint signals emitted by hydrogen, cosmologists will continue to apply their models of the universe's evolution to interpret these signals in a broader context. The 21 centimeters signal is not just a simple data point, it is a messenger from the very dawn of the universe, carrying with it information about the conditions and events that occurred billions of years ago. By combining observational data with theoretical models, we can begin to understand how these signals fit into the larger story of cosmic history, from the Big Bang to the present day. As we move forward with these ambitious projects and collaborations, it is clear that we are on the cusp of a new era in cosmology. The ability to directly study the early universe using the 21 centimeters hydrogen line will open up new frontiers in our understanding of the cosmos. We will gain unprecedented insights into the formation of galaxies, the evolution of stars, and the origins of the very elements that make up the universe. We will be able to track the development of the universe's largest structures, such as clusters of galaxies and supermassive black holes, and uncover the secrets of dark matter and dark energy. Moreover, the study of the 21 centimeters signal has the potential to revolutionize not just our understanding of the cosmos, but also our grasp of fundamental physics. From exploring the nature of gravity to understanding the behavior of quantum fields at cosmological scales, the 21 centimeters line may provide key evidence that could lead to new breakthroughs in physics. Some have even speculated that the 21 centimeters signal could offer a window into the mysterious realm of quantum gravity, where the forces of quantum mechanics and general relativity converge. This is the holy grail of modern physics, and the 21 centimeters hydrogen line might just be the key that unlocks this enigma. Looking to the distant future, the study of the 21 centimeters hydrogen line could play a pivotal role in addressing some of the most profound questions facing humanity. What is the nature of the universe? How did it begin? What is the fate of all the stars and galaxies? By studying the 21 centimeters signal, we may uncover the very foundations of reality, And as we continue to expand our understanding, the mysteries of the universe will become less enigmatic, revealing the grand narrative of our cosmic origins. It is not just about the signals we detect or the data we gather. It is about our unyielding curiosity to understand the universe and our place within it. The quest to unravel the mysteries of the cosmos is a journey that has captivated human imagination for millennia. And as we peer deeper into the vastness of space, the 21 centimeters hydrogen line stands as one of the most promising pathways to uncovering the most profound and awe-inspiring truths about the universe. As we delve deeper into the implications of the 21 centimeters hydrogen line, it's important to consider how the discoveries we make might shape the future of space exploration and our understanding of cosmology. The 21 centimeter signal is a unique cosmic fingerprint that holds information not just about the early universe but also about the way the universe evolved into the one we see today. By studying it, we aren't just peering back in time, we are also gaining insights into how the universe will continue to evolve. One of the most intriguing aspects of the 21 centimeter signal is its potential to shed light on the epoch of reionization. This period, which occurred between 13 billion and 14 billion years ago, marks the time when the first stars and galaxies began to form. These early stars emitted light that ionized the surrounding hydrogen gas, effectively reionizing the universe. The 21 centimeters hydrogen line provides a window into this era because the hydrogen atoms during this time were still predominantly neutral. The signal emitted by these neutral hydrogen atoms is what we now call the 21 centimeters line, and studying it can give us a detailed picture of the conditions that prevailed during this critical phase in cosmic history. The reionization epoch is a crucial period in the history of the universe because it marks the transition from a dark, cold, and opaque cosmos to one filled with light and structure. Before reionization, the universe was a homogeneous soup of gas, mostly hydrogen and helium, with no stars, galaxies, or complex structures. The process of reionization not only made the universe more transparent, but also set the stage for the formation of the galaxies, clusters, and supermassive black holes that we see today. It's also during this epoch that the first hints of dark matter may have begun to manifest. The 21 centimeters signal has the potential to provide us with a roadmap of this formative time, allowing us to understand when and how reionization occurred and how the universe transitioned from a smooth state to the lumpy, structured one we see now. The mystery of the reionization epoch is far from solved. We know that it began when the first stars started forming, but we don't know exactly how long it took or what role other factors, like the formation of black holes or the presence of dark matter, played in this process. By studying the 21 centimeters hydrogen line, astronomers are hoping to answer these questions. For example, some theories suggest that the first stars formed in small, isolated regions and slowly merged into larger galaxies. Other theories propose that black holes may have played a more active role in reionizing the universe by producing intense ultraviolet radiation. Whatever the answer may be, the 21 centimeter signal is a vital tool for unlocking this mystery. As we attempt to reconstruct the history of reionization, we also find that the 21 centimeter signal offers a cosmic probe of the distribution of hydrogen throughout the early universe. The signal emitted by hydrogen at various points in time tells us about the density fluctuations of the gas, the temperature of the surrounding environment, and even the magnetic fields present in these distant regions. These fluctuations, or variations in the density of hydrogen, are critical for understanding how the first galaxies formed and how matter began to coalesce under the influence of gravity. The 21 centimeter signal serves as a cosmological census of the hydrogen distribution, allowing us to map the distribution of matter across vast regions of space. In addition to helping us understand the evolution of the early universe, the 21 centimeter signal could also provide crucial insights into some of the most enigmatic aspects of modern cosmology, such as dark matter and dark energy. Both of these components make up about 95% of the universe's total mass energy content, yet they remain largely invisible and undetectable by traditional means. Dark matter, which is thought to account for the missing mass in galaxies and galaxy clusters, could leave subtle traces in the 21 centimeters signal. If dark matter interacts with normal matter in ways we don't fully understand, this interaction might influence the 21 cm signal in detectable ways, allowing us to indirectly study dark matter's properties. Similarly, dark energy, which is believed to be responsible for the accelerated expansion of the universe, might also have an impact on the 21 cm signal. The expansion of the universe affects the way that light and radiation propagate through space, and the accelerated expansion could alter the way we observe the 21 cm hydrogen line. By studying how the signal changes over time, we could gain further insights into the nature of dark energy and how it is influencing the evolution of the cosmos. Looking forward, the detection and analysis of the 21 cm signal could play a pivotal role in guiding future space exploration missions. As we build more advanced telescopes and refine our methods for interpreting the 21 cm signal, we will gain a more detailed understanding of the universe's evolution. This knowledge will, in turn, guide our future efforts to explore the cosmos. For example, the James Webb Space Telescope, JWST, which is designed to observe distant galaxies and stars in infrared wavelengths, will complement the work done by radio telescopes studying the 21 cm hydrogen line. By combining data from multiple observatories and telescopes, we can build a more comprehensive picture of the universe's history and evolution. The study of the 21 cm hydrogen line is not just about answering scientific questions. It is about pushing the boundaries of human knowledge and exploring the deepest mysteries of the universe. Each new discovery brings us one step closer to understanding how the universe began, how it has evolved, and where it is headed. It's a journey that requires patience, collaboration, and innovation. As we move forward, we will undoubtedly encounter more challenges, but we will also uncover new and exciting possibilities for understanding the cosmos. The 21 cm hydrogen line is a cosmic relic, a faint echo of the universe's infancy. Yet, it holds within it the potential to answer some of the most profound questions in modern science. It is a key that could unlock the mysteries of reionization, the formation of the first stars and galaxies, and the nature of dark matter and dark energy. As we continue to develop the technology to detect and study this signal, we are embarking on a journey that will reshape our understanding of the cosmos and our place within it. For all its mysteries, the 21 cm hydrogen line also serves as a reminder of the vastness and complexity of the universe. As we seek to uncover the secrets of the universe's earliest structures, we are reminded of how much we still have to learn and how much potential there is for discovery. The journey to understand the 21 cm signal is just beginning, and the discoveries we make in the years to come may forever change our understanding of the cosmos. As we continue to explore the depths of the 21 cm hydrogen line, it's crucial to recognize just how significant this discovery is for the future of cosmology. It allows us to look back in time to an era when the universe was still in its infancy, shedding light on a period that is otherwise largely invisible to us. The ability to study this faint signal, emitted by neutral hydrogen, offers a wealth of opportunities to understand cosmic history at a level that was once unimaginable. Every new insight gleaned from the 21 cm signal brings us closer to solving the mysteries of the early universe, mysteries that, until recently, seemed far beyond our reach. One of the most exciting possibilities the 21 cm signal presents is its potential for mapping the large-scale structure of the universe. While galaxies and clusters of galaxies are relatively easy to observe, the intergalactic medium, the vast expanse of gas between galaxies, remains difficult to study. This gas is often too faint to be detected by traditional telescopes. However, the 21 cm hydrogen line offers a unique method for mapping this invisible part of the universe. By observing how the 21 cm signal interacts with the surrounding gas, scientists can trace the distribution of matter across vast regions of space, filling in gaps in our understanding of the universe's structure. The signal also holds the potential to answer a number of fundamental questions about the cosmological model itself. For example, by studying the variations in the 21 cm signal across different regions of the sky, scientists can investigate the cosmic microwave background (CMB), the afterglow of the Big Bang, and its relationship to the formation of structures in the universe. The CMB provides a snapshot of the universe just 380,000 years after the Big Bang, but the 21 cm signal allows us to peer even further into the past, potentially revealing details about the very first moments of the universe's existence. Another fascinating aspect of the 21 cm signal is its potential to explore the evolution of cosmic inflation, a theory that proposes a period of rapid expansion in the moments immediately following the Big Bang. While inflationary models have been supported by indirect evidence, such as the distribution of galaxies and the CMB, direct evidence for inflation remains elusive. The 21 cm signal could provide a new way to test the validity of these models, offering insights into the rapid growth of the universe during its earliest moments. If inflation did indeed occur, it would leave an imprint on the 21 cm signal, providing a crucial piece of evidence for this theory. The ability to study the cosmic dark ages, the period after the Big Bang when the universe was mostly filled with neutral hydrogen and helium, through the 21 cm signal is equally exciting. This era, which began about 380,000 years after the Big Bang and lasted for millions of years, is difficult to observe directly. The 21 cm signal, however, allows us to probe the conditions that existed during this dark time. By studying how the signal evolves over time, scientists can gain valuable insights into the processes that led to the formation of the first stars, galaxies, and other structures in the universe. This could help us answer fundamental questions about the transition from a smooth, homogeneous universe to one filled with galaxies and other structures. The technology needed to detect the 21 cm signal is advancing rapidly. Over the past decade, astronomers have developed increasingly sensitive radio telescopes capable of picking up the faint signal from across the universe. Projects such as the Low Frequency Array, LOFAR, the Square Kilometre Array, SKA, and the Hydrogen Epoch of Reionization Array, HERA, are pushing the boundaries of what's possible in terms of detecting and studying the 21 cm hydrogen line. These projects are designed to detect the faintest of signals, offering a deeper understanding of the universe's earliest moments. As these arrays come online and begin collecting data, we can expect a revolution in our understanding of the cosmos. What's especially exciting is the potential for future collaboration between different types of observatories. While radio telescopes focused on the 21 cm signal are essential for studying the early universe, optical, infrared, and X-ray telescopes can provide complementary data. For example, the James Webb Space Telescope, JWST, with its unprecedented ability to observe distant galaxies in infrared light, will work alongside radio telescopes to provide a more comprehensive view of the universe. By combining data from different wavelengths, scientists can create a more complete picture of the evolution of the universe, from the birth of the first stars to the formation of galaxies and beyond. The exploration of the 21 cm hydrogen line also opens up new possibilities for intergalactic communication and the detection of extraterrestrial life. While this may sound speculative, it's not as far-fetched as it might seem. If the 21 cm signal can be used to map out the early universe and its structures, it could also help us identify other potential sources of radio emissions in distant galaxies. In the future, astronomers could use similar techniques to search for signals from alien civilizations. The Search for Extraterrestrial Intelligence, SETI, has traditionally focused on detecting narrow-band signals in the radio spectrum, but the 21 cm signal may offer a new avenue for detecting life beyond Earth. The potential for cross-disciplinary research is another exciting aspect of studying the 21 cm hydrogen line. As we continue to gather more data and refine our techniques, we can expect to see collaborations between astronomers, physicists, and cosmologists, as well as researchers in fields such as computer science and data analysis. The complexities of the 21 cm signal and the vast amounts of data that must be processed make this an ideal area for interdisciplinary work. By combining expertise from a wide range of fields, we can accelerate our understanding of the universe's history and evolution. Of course, we must also acknowledge the challenges that come with studying the 21 cm hydrogen line. The signal is incredibly faint, and isolating it from the background noise of the universe requires state-of-the-art technology and sophisticated techniques. The universe is filled with a myriad of radio signals, many of which come from sources within our own galaxy. To detect the 21 centimeter signal, astronomers must carefully distinguish it from all the other noise, which requires extremely sensitive equipment and careful data processing. This is one of the reasons why the detection of the 21 centimeter signal is still in its early stages, despite its immense potential. Moreover, the 21 centimeter signal is not a simple, straightforward signal. It carries with it a wealth of information about the universe's history, but this information is embedded in a complex set of interactions that are not always easy to decipher. The signal's strength, shape, and evolution over time are influenced by a wide variety of factors, including the density of hydrogen, the temperature of the gas, and the presence of cosmic structures like galaxies and black holes. Decoding the 21 centimeter signal requires a deep understanding of these factors and the ability to model the universe's evolution in precise detail. Despite these challenges, the rewards are immense, and astronomers are already making great strides in understanding the mysteries hidden within the 21 centimeters line. The 21 centimeters hydrogen line is a unique and invaluable tool for unlocking the secrets of the early universe. Its potential to reveal insights into the formation of the first stars, the epoch of reionization, the large-scale structure of the universe, and the nature of dark matter and dark energy is immense. As technology advances and our ability to detect and study the 21 centimeter signal improves, we will undoubtedly uncover new and exciting revelations about the universe's history and future. The 21 centimeter signal is a cosmic relic, a faint echo from the past that holds within it the key to understanding the birth and evolution of the cosmos itself. The study of the 21 centimeter signal is just beginning, and the journey ahead promises to be one of the most exciting and transformative in the history of science. As we continue to peer into the depths of the universe, using this elusive signal to guide our way, we will uncover new truths about the cosmos and our place within it. It is an endeavor that will require the collaboration of scientists from around the world, the development of cutting-edge technology, and the imagination to explore the unknown. But with each step forward, we come closer to answering some of the most profound questions in all of science. The study of the 21 centimeters hydrogen line is also shedding light on the enigmatic processes that took place during the cosmic dark ages, a period that has traditionally been a black hole in our knowledge of the universe. This epoch, spanning from roughly 380,000 years to about 1 billion years after the Big Bang, is often seen as a mysterious and difficult-to-understand chapter in the universe's early history. During this time, the universe was mostly devoid of stars, galaxies, or any luminous objects that could provide an easily observable signal. However, the faint yet pervasive signal of neutral hydrogen, traced by the 21 centimeters emission line, offers a rare glimpse into this hidden era. One key mystery that astronomers are attempting to unravel is how the very first stars, known as population 3 stars, formed during the cosmic dark ages. These stars were composed almost entirely of hydrogen and helium, the primary elements present in the early universe. The presence of these stars is critical to understanding the reionization process, which marks the transition from a neutral to an ionized universe. By studying the evolution of the 21 centimeter signal during this time, scientists can gain insight into how and when the first stars ignited, how they affected the surrounding hydrogen gas, and how the universe began to evolve toward its present state. The period of reionization itself remains one of the most exciting and hotly debated topics in cosmology. This was a time when the first stars and galaxies began to emit ultraviolet radiation, which gradually ionized the hydrogen gas that filled the universe. The exact timing and mechanisms of reionization are still unknown, but the 21 centimeters hydrogen signal can provide crucial information to answer these questions. By analyzing the way the signal evolves over time, astronomers can determine when and how the process of reionization occurred, and what role the first stars, galaxies, and black holes played in this monumental shift. The detailed study of the 21 centimeter signal will help unravel the complex interactions between matter, radiation, and gravity that shaped the early universe. Interestingly, the 21 centimeters hydrogen line also holds the potential to revolutionize our understanding of dark matter and dark energy, two of the most mysterious components of the cosmos. While these phenomena have been theorized based on their gravitational effects on visible matter, they remain largely invisible to current observational methods. The 21 cm signal offers a unique way to probe the effects of dark matter in the early universe. This could provide the first direct evidence for dark matter's influence on cosmic structures and give us new insights into how it interacts with normal matter. For example, dark matter is believed to have played a crucial role in the formation of the very first structures in the universe. Its gravitational pull helped to shape the distribution of matter in the early universe, leading to the formation of the first galaxies and clusters of galaxies. By studying the 21 cm signal in regions of the universe where dark matter is thought to have had a significant impact, astronomers could begin to map its distribution and better understand its properties. This would be a monumental step forward in our quest to understand the nature of dark matter and its role in shaping the cosmos. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, may also leave traces in the 21 cm hydrogen signal. By studying the evolution of the signal across vast regions of space, scientists could look for subtle patterns that could reveal the effects of dark energy on the growth of cosmic structures. Although dark energy remains largely unexplained, the 21 cm signal could offer an entirely new approach to investigating this enigmatic phenomenon, bringing us one step closer to uncovering the true nature of the universe's most elusive force. The technology that allows us to observe the 21 cm hydrogen line is continually advancing, making it possible to explore the early universe with greater precision and depth than ever before. Over the last few years, numerous radio observatories have been built or upgraded to detect the faint 21 cm signal, and as these instruments come online, our ability to probe the cosmos in this way continues to improve. The Low-Frequency Array, LOFAR, the Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SK, are among the key projects pushing the boundaries of 21 cm detection. Each of these projects aims to map the early universe with unprecedented sensitivity and resolution. LOFAR, for example, has been able to detect the 21 cm signal from distant galaxies, helping astronomers investigate the process of cosmic reionization. The HERA project, on the other hand, is focused on studying the 21 cm signal from the era of the cosmic dark ages, aiming to uncover the first steps in the formation of stars and galaxies. Meanwhile, the SKA, one of the largest and most ambitious radio telescope projects ever conceived, holds the potential to offer detailed images of the universe's earliest moments. With these state-of-the-art instruments in play, we're entering an era where the mysteries of the early universe will gradually be revealed. The role of future space telescopes cannot be understated either. While ground-based observatories like LOFAR and HERA have made tremendous strides in detecting the 21 cm signal, there is a growing interest in launching space-based missions that can observe the hydrogen line with even greater clarity. Space telescopes have the advantage of being free from the interference of Earth's atmosphere, which can distort or obscure faint signals. In particular, the James Webb Space Telescope, JWST, launched in December 2021, will be an important tool for studying the early universe, including the 21 cm hydrogen signal. Although the JWST is primarily designed for infrared observations, it will complement radio telescopes in studying the large-scale structure of the universe, the formation of the first stars, and the processes that led to reionization. The combination of radio observatories and space telescopes will provide a holistic view of the universe's evolution, from its earliest moments to its current state. By cross-referencing data from different observatories, astronomers can piece together a more complete and accurate picture of the cosmos. As our observational techniques improve and new instruments come online, we are bound to discover even more about the 21 cm hydrogen line and its implications for our understanding of the universe. As these efforts continue, one of the greatest challenges will be to refine our understanding of the intricate physics behind the 21 cm signal itself. The signal's faint nature and the complex interactions that influence it mean that it can be difficult to interpret. Factors such as cosmic inflation, the distribution of hydrogen, and the influence of dark matter all play a role in shaping the signal, and unraveling these contributions requires sophisticated modeling and analysis. As the data continues to pour in from radio telescopes and other observatories, we can expect a constant refinement of our theories and models, helping to make sense of this invaluable signal. In the end, the 21 centimeters hydrogen line is more than just a cosmic relic. It's a window into the earliest moments of the universe, offering insights into the birth of galaxies, the formation of the first stars, and the evolution of the cosmic landscape. It's an essential tool in our quest to answer the fundamental questions about the universe. How did it begin? What is it made of? What will its future hold? The ability to study the 21 centimeters signal represents a giant leap forward in our understanding of the cosmos. As we continue to probe this mysterious signal, we are not only uncovering the story of the early universe, but also laying the groundwork for the next great leap in cosmological discovery. What we learn from the 21 centimeters hydrogen line today will influence the course of astronomy for generations to come. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.